we began the second day of our conference. I hope it will be no less interesting than yesterday. Okay, our first speaker, Dr. Shanta Kita, Tohoku University, Japan, optimization of ultrasonic spot welding parameters for aluminum, copper, and aluminum nickel similar and dissimilar joints. Please.
Okay, thank you for your introduction. First of all, I'm Shunto Kita from Tohoku University, Japan. First of all, I'd like to express my deep appreciation for this opportunity to talk in this wonderful conference in Ukraine, and also for Dr. Schwab for invitation for me. And I'm very happy to see you guys in safe and studying together actively in this, even though in this difficult situation around you. Okay, I'm going to start my talk. Today I would like to talk about the optimization of ultrasonic spot welding parameters for aluminum copper. Sorry, aluminum copper, and aluminum nickel similar and dissimilar joints. Okay. As you may already know, copper is widely used in electrical and electronic components in many industrial fields. Also, however, due to the heavy weight for copper itself, the replacement of copper with aluminum has been promoted for the weight reduction of these components. In addition, copper is sometimes plated by nickel to ensure the corrosion resistance. Therefore, dissimilar joining of aluminum to copper and aluminum to nickel is required for these practical applications. And there is some problems with conventional dissimilar welding method, such like the formation of brittle intermetallic compound and large residual stress due to the difference in physical properties, such as the thermal expansion coefficient, and also severe deformation at the interface. Ultrasonic spot welding is one of the solid-state welding methods using pressure and ultrasonic vibration. As you can see in this schematic image, the ultrasonic welding machine mainly consists with the two parts, which is the anvil and sonotrodes. As you can see in this schematic, the specimens will be in between the anvil and sonotrode. And on the starting of the welding method, the sonotrode will be loaded on the specimen, and the ultrasonic vibration will be induced to the interface of two welded materials. And frictional heat and deformation will make the solid-state joining of two materials. There are some advantages of ultrasonic spot welding, such as the low energy consumption and low distortion, and also high efficiency, short welding time. And there are some variables such like welding time and welding pressure and amplitude. In previous studies on ultrasonic spot welding of these materials, some influencing factors such as the welded area, welding energy, or IMC layer formation, and also recrystallization, influencing the joint strengths. When we think these parameters systematically, there is the combinations parameters such like the materials combinations and welding parameters combinations. And it affects the characteristics of the welds, such like a welded area or intermetallic compound or appearance with specimens and microstructures. And these factors will be resulted in properties such as strength and hardness. In order to get the good property in joint, we need to to understand how these materials combinations and welding parameters affect the characteristics of the joint. Therefore, the objective of this study is to examine the effect of welding parameters on microstructure and joint strength in ultrasonic spot welding of aluminum copper, and aluminum nickel. Here is the experimental procedures. Specimens used in this study is the pure aluminum sheet and copper sheet and nickel sheet with thickness of 1 millimeters. Chemical composition are shown in this table. These specimens are wrapped like this with the overlap for 14 millimeter, and the front load size is the 6 millimeter to 6 millimeters. There are main welding parameters. Frequency of the ultrasonic vibration is around 20 kilohertz, and the welding pressure is varied from the 0.2 to 0.4 megapascal. And welding times are varied from the 0.2 to 1.2 second. Amplitude are also varied from the 26 to 52 micrometers. And after joint was produced, these mechanical properties are evaluated by the tensile shear test and viscous hardness tests. And the welded area were measured like this, and we took the cross-sectional interface by optical microscope and measure the length of the welded area and unwelded area, and we get the ratio of these two areas as the welded ratio. And temperature measurement are done with these schematics with K-type thermocouple, and microstructure was observed with SEM-EDS analysis and also USD analysis in the cross-section. And let me move on to the result. This slide shows the effect of welding parameters on tensile shear load or in each materials combination. These process windows, the horizontal axis shows the welding pressure, and vertical axis shows the amplitude of ultrasonic vibration. Here is the aluminum and aluminum copper and aluminum nickel result. In all the materials, two typical fracture appearance was found after tensile shear test. One is the fracture at interface, as shown in the green line in these graphs. And the second one is the fracture on aluminum side, as shown here. Aluminum upper sheet was broken in these conditions. In all material combinations, fracture occurred in the upper aluminum sheet under the condition of 0.3 megapascal with the 52 micrometer amplitude, resulting in relatively high strength. So I choose these parameters here, and here. I choose these parameters for further investigations. This is the relationship between the welded ratio and tensile shear load in each materials combination. Ultimate tensile shear load increased with increasing welded ratio, and excessive welding conditions result in the low tensile shear load regardless of high welded ratio. And this is about the effect of welding time. This slide shows the ultimate tensile shear load in different welding times in each material combinations. The maximum load increased with the increase in welding time, then decreased. In aluminum nickel joint, the range of welded times that result in high strength was narrower compared to aluminum and aluminum copper. So it is difficult to adjust the optimum condition in aluminum nickel. This is the appearances of the joint with same welding parameters with 0.3 megapascal pressure and 52 micrometer amplitude and welding time for 0.6 seconds. Although the welding parameter is exactly the same, only in the aluminum nickel joint, severe deformation of the upper aluminum sheet was observed, as shown in this image. So I compared the temperature history and the sonotoroid penetration within these different combinations of materials. In these graphs, the solid line shows the temperature history during the welding, and the broken line shows the penetration depth of the sonotoroid from the upper sheet. And you can see that in aluminum and aluminum copper, the temperature goes up with the penetration depth increasing. But the penetration depths are within stable value in the 0.2 seconds or so. On the other hand, in aluminum nickel, the temperature goes up with the penetration depth like aluminum, the other materials combination, but from the 0.4 to 0.6 seconds, the a rapid increase of the temperature and the severe deformation with the penetration rapid increasing penetration depth was observed. So I analyzed the deformation behavior in the joint in different materials combinations by EBSD. First of all, this slide shows the base material of aluminum upper sheet from the loading direction. This is the IQ map and IPF map, and this is the pole figure for 111 and 101 within the maximum intensity with these pole figures. As you can see, typical loading texture was found in the base material. Oh, sorry. Some Japanese remained. Japanese language remained, sorry. This slide shows the cross-section IPF maps of the aluminum copper, and aluminum nickel IPF maps. There are two, here is the center of the wells is here. And here is the edge of the sonotoroids, under edge of the sonotoroids. As you can see here, there is some regions with the characteristical microstructures. So I divided the two areas from these images. One is the top center of each wells is region A, and also interfacial area is region B within aluminum and aluminum copper. This is the pole figures for these observed areas. In aluminum in top center. In aluminum top center, as you can see, texture was slightly changed from the loading texture. And on the interfacial regions, the texture was very weak, is 3.9 in intensity compared with the 9.1 intensity in base material. So in this interface area, weak texture is because of the entire top sheet was weakly deformed together. In aluminum copper, in region A top center region, no significant change from rolling texture was found. But on the other hand, on interfacial area, significant GOSS texture, which is related with the recrystallized microstructure, was found. Therefore, I thought that the local heat and deformation induced is concentrated on the interfacial area in this aluminum copper joint and resulted in recrystallization. And in aluminum nickel, as you can see in this IPF map, entire region was severely deformed due to the high penetration depth of the sonotoroid. And therefore, there is only one region I divided. Entire top sheet has a strong texture with shear direction to the vibration direction, and severe deformation in elevated temperature are considered in this aluminum nickel joint. And this is the similar IPF maps in different welding times. This is from the 0.4 and this is from 0.6 seconds. In shorter welding time, we can see that even in aluminum nickel joint, we can see the region A and B different regions, which is very similar to the aluminum copper with 0.6 seconds, which is the I presented in the last slide. GOSS ghost structure is found in region B interfacial region in 0.4 seconds, but in 0.6 seconds, the severe shear deformation was found. Therefore, in the aluminum nickel joint, rapid deformation occurred between 0.4 and 0.6, which is corresponds with the temperature and deformation results. So from this result, I have some discussion with these schematics. First of all, thermal conductivities on these materials, aluminum, copper, and nickel, are shown here. Thermal conductivities copper is, as you already know, very high. Therefore, in aluminum copper, the frictional heat avoided to the lower sheet and anvils within very rapidly. Therefore, the thermal intensity and the temperature goes on not very high temperature. But on the other hand, in aluminum nickel joint, the thermal conductivity of nickel is very low compared with the other materials. So the heat generated by frictional heat are concentrated on the aluminum upper sheet, and it makes the severe deformation on the later seconds of the joining. I think that is because the severe deformation was found only in aluminum nickel joint. Here I conclude my presentations. Two typical fracture modes in the tensile shear test were found for all materials combinations. One is the fracture at the bonding interface, and the second is the fracture of the upper aluminum sheet. The range of the welding times resulting in high maximum shear load was narrower in aluminum nickel joints compared to the other material combinations. The significant deformation of the upper aluminum sheet caused by the rapid temperature rise between 0.4 to 0.6 seconds led to the decrease in maximum tensile shear load in aluminum nickel joint. Thank you very much for your kind attention. I'm very happy to have your questions and answers from audience.
Dr. Takim. Thank you for interesting report. It's time to questions.
question. Thank you for your report. What technology give more higher strength of joints? Conventional spot welding or ultrasonic spot welding?
Strengths of ultrasonic welding. When we get the interfacial fracture, maybe we need to improve the strength. And but in the sorry, I don't know. Sorry. In the conditions with the higher strengths, we get the base material fracture. So maybe with pure aluminum, the strength of the ultrasonic welding is adequate the using in these material combinations. But in order to improve, get more, maybe we need to analyze the deformation behavior and also the on the oxidation of the fragmentation of the oxides in the interface. We need to understand these phenomena during the ultrasonic welding.
Thank you.
Thank you very much.
Thank you for your talk. And question is, do you observe any resonance effect during welding? So for different shapes and thicknesses, you can get some harmonics, and may this lead to some effects on strengths or weldings?
Harmonics. Maybe you are. Sorry, my EBSD map is too heavy, so changing pages is sometimes very slow. Okay, I think you are talking about this slide here. In severe deformation of upper plate and resonance.
I mean that for thin plates, if you apply to them ultrasonic treatment, and for some frequency, for some resonance.
Okay. In this study, I didn't change the frequency of ultrasonic vibration. But when we change the ultrasonic vibration, maybe the frictional heat generated in the interface will be changed. So maybe welding time or optimization process window will be changed.
Okay, thank you.
Thank you for your report. I have a question about your ultrasonic power source. What was the frequency and what was the power?
Frequency is around 20 kilohertz. So to 20,000 times in sec. And the power source, sorry, I don't know about the specific source of the ultrasonic generator. So sorry, I don't know about the equipment details. But the frequency is around here.
Okay, more questions? If no, please stand closer on more.
Thank you very much.
Okay, our next speaker, Dr. Svetlana Maximova, from Electric Welding Institute. brazing of titanium alloy TA15.
Good morning. Good morning, dear colleagues. I would like to introduce our research on brazing of titanium alloy TA15. Moving to our Ничего у меня не получается. Next. Ничего не получается. Ну, так я так и делала. Ладно. Moving on to our outline of our presentation, we will begin with the introduction, where we will provide an overview of the objectives of this research and the relevance of the materials involved. Subsequently, we will consider the investigations method and material employed to conduct our study, including the brazing process parameters and characterization techniques utilized. Next, we will discuss the obtained results, analyze the structure and strength properties of the brace joint fabricated from titanium alloy TA15. Let's get started with our introduction. Please, next. The titanium alloy TA15 has garnered significant attraction as a material for fabrication of aerospace structures, gas turbine blades, and various other applications. This interest stems from the exceptional high temperature mechanical and technological properties with remain effective at temperature up to 500 and 600 degrees. Such capabilities are critical environments that demand high performance, like aerospace and energy sectors. Nevertheless, it is important to highlight that the brazing process for this alloy has not yet been sufficiently studied, leaving gaps in our understanding of its behavior and performance during joint formation. Please, next. The brazing ranks among the leading techniques for joining titanium alloys due to this ability to produce strong, hermetically sealed and heat-resistant joints. These characteristics are essential for industries such as aerospace, energy, automobile manufacturing, electronics, and electrical engineering, where the integrity of concentrations can significantly impact overall system performance. For brazing to be effective, the technology and filler metals employed must ensure that the resulting braze seams exhibit properties that are comparable to those of the base materials. Such maintaining structure, integrity, and performance under operation conditions. The specific nature of titanium alloys, including TA15, decreases the critical temperature time limits for brazing cycles. These limits are particularly important to avoid undesirable changes in microstructure and properties of the base materials, which can comparable the joint's performance. Key factors including these limits include presence of alpha-beta transformation. This transformation occurs at 882 degrees and can lead to significant alterations in the mechanical properties of the alloy. The phenomenon negatively impacts the ductility of the base metal, and the larger grain size can reduce the material's ability to deform under stress. And titanium is known as the high reactivity, which can promote the formation of brittle intermetallic compounds within the braze joint in the heat-affected zone. These compounds can compose the ductility and toughness of the joints, making it more susceptible to cracking or failure under mechanical loads. Next, please. Typically, brazed seams from titanium alloys exhibit a heterogeneous structure composed of the solid solution matrix based on titanium and intermetallic compounds. However, by optimization the temperature and time parameters of the brazing cycle, it is promised to achieve excellent mechanical and corrosion properties of the braze joint, both at room and evaluated temperature. The aim of our study was to assess the effect of the time parameters in the brazing process on titanium 15 alloy, on the formation of the structure and mechanical properties of the braze joints, as well as to investigate the influence of base metal surface preparation on the spreading of the brazing filler metal. Next, please. During the experiments, the titanium alloy was used as the base metal, and for brazing filler metal, we used the system titanium zirconium in cast state to evaluate the effect of base material surface preparation on the spreading of the brazing filler metal. Samples were used that were mechanically cleaned and chemically attached in mixture of two acids, nitric and hydrofluoric. Brazing was carried out in the vacuum furnace with radiation heating. Metallographic studies were conducted using scanning electron microscope. And mechanical properties we study at room temperature. Next, please. And the first step of our research was to evaluate the impact of temperature time parameters during the heating cycle on the spreading of the brazing filler metal on the structure on titanium alloy. A series of experiments was conducted at 3 different temperatures, 990, 915, and 1000 degrees. And holding time was 15 minutes. The results of our study of the spreading behavior of the titanium zirconium brazing filler metal was shows that the increase the heating time, heating temperature from 900 to 900 degrees significantly increase the spreading area of the brazing filler metal. This picture you can see the specimen which we study by electronic microscope. It should be noted that the wetting contact angles of the filler metals on the base materials range from 20 to 25 degrees. It's nice for brazing process. Additionally, there is no significant dependencies of such parameters on the brazing temperature. And furthermore, during the spreading process, erosion of the base materials occurs due to the interaction between the molten filler and substrate, and resulting in erosion depth on approximately 19 till 100 micrometers. This picture you can see the contact angle between base metal and filler metal, and this interface area, and it was at 900 degrees, and this was the temperature more higher, and we can see that contact and we have smaller. It's nice for brazing. The depth remains relatively consistent, even the temperature is evaluated to 100 degrees. Please, next. Moreover, it has been found that for samples subjected to mechanical cleanness, the spreading area is 10-20 greater than that of samples proceedings using standard methods with involve etching in solution of exit mixture. Furthermore, during the investigation of the spreading behavior of the brazing filler metal on the titanium alloy, it was observed that the heating temperature increased to 950 was more spreading area was greater than at temperature 900. However, the further increases in temperature, the rate of growth in the spreading area slowed considerably. Please, next. In this picture, you can see the microstructure, our specimen, which we produced during 15, 13, and 16 minutes. To evaluate the influence on the time of the cycle on the structure and mechanical properties, we study this specimen and we observed the bracing in all cases are derived in the usually defect-free. It is important to note that fillet region of the brace joint, even we longest holding time, 16 minutes, exhibit area with cast structure, with, which is characteristic of the brace system. At this picture, we can see the microstructure of brace seam, and at this column, we have microstructure of fillet region. And in fillet region, we have more quality of metal, melting metal, and we have another structure than in bracing seam. In brace seam, even the natively short holding time, 15 minutes and longer, the interdiffusion process occurring during bracing prevent the formation of areas in the cast structure of eutectic inclusions. The brace showing predominantly consist of alpha phase, it's dark disoriented subgrains that typically form of course lamellar structure contributed to the overall strength and integrity of the joints. And beta phase, light colored layers filled with the needle-like beta phase structures enriched with another elements which we have in bracing filler metal, such copper and nickel, which enhance the mechanical properties of the joints. It has been found that the geometric characteristics of both the lamellar and beta layers depend significantly on the time parameters of the bracing site. Increasing the holding times leads to results in changes in the size of distribution of these phases, which can ultimately affect of the mechanical properties of brace joints. Please, next. And this, here you can see the microstructure of bracing joint, which we produced at temperature 900 degrees, and the holding time was 15 minutes. We can see the structure consists of wide disoriented subgrains of the alpha phase and broad layers filled with needle-like phase alloyed with other components of the filler metal. The increasing concentration of these elements, as confirmed by electronic beam scanning, indication this presence. You can see the distribution of different elements which consist our bracing filler metal. According to the literature date, these elements are known to lower the alpha-beta transition temperature, facilitates the formation of a martensit-like needle phase. The weight of the brace seam, in this case, we have about 70-80 micrometers. Please, next. When increase the holding time to 30 minutes, the weight of the seam expands to 100 micrometers, and the amount of alpha phase in the release. Considerably, the weight of needle-like beta phase decreases. You can see here another element distribution, long, the of white our brazing sim. Please, next slide. We increase the holding time to 60 minutes. Next. Uh, 20. 12. Опустим один. 12, ладно. We have seen, I would like to, yes. Further increase of holding time, in further increasing for holding time, we have the homogeneity microstructure of brazing sim and more homogeneity distribution of other elements which contain our filler metal. We extending this time for prepare the special samples for mechanical properties. We can see this homogeneity of brazing sample degrees. It's very nice for mechanical properties of the brazing joints. Next, please. At this picture, we can see the microstructure in our three variant of time, and we can see the white of brazing sim white of brazing sim became more greater when we decrease, when we increase the brazing time. It is known that wider bonding area is specifically beneficial in applications subjected to site or dynamic loads, as it's distributes mechanical stress more effectively, this minimizing the likelihood of joint failure. And please, next. And this result, this picture, you can see the result of mechanical test and our specimen for study mechanical properties. We can see the correlate with the finding from metallographic studies indicated that increasing the holding from 15 to 60 minutes enhances the homogeneity of the braid seam structure and increase the shear strength by 15%. Next, please. Conclusions. In this study, we examined the effect of holding time during vacuum high temperature brazing on the structure and mechanical properties of joints made from TA15 alloy with brazing filler metal of the titanium zirconium system. And the investigation into spreading of our brazing filler metal on the titanium substrate indicates that prior mechanical processing of the base metal enhances the spreading area by 10–20% compared to samples treated with etching in the exit mixture. Additionally, it was found that increasing the heating temperature from 900 to 950% result in a 10% increase in the spreading area of the brazing filler metal. And micro spectroscopic analysis showed that extending the temperature leads to nearly twofold increase in the white holding time from 15 to 60 minutes of the braid film from 16 to 162 micrometers, and improve the homogeneity of the structure and rises shear strength by about 15% in overlap press joints. Thank you for attention.
Thank you for your report. Any questions, please?
Thank you very much, Selena. Very interesting work. My question is, what about environment for brazing tips of vacuum?
Vacuum brazing used in very wide in different industries. Vacuum, we vacuum. We made our investigation in vacuum chamber.
Yes, and date, what is date about vacuum?
Date 10 minus 3 MPa
Pascal.
Pascal.
Thank you very much.
One more question. Thank you for your information. What is the optimal temperature for brazing, for your opinion, or as a result of your investigation?
Because we have transformation at temperature 8,082. Yes, 100. 882 degrees. It's a better temperature. We have 900, maybe 950. But when we increase the temperature, we have more big зерна. Grain, yes.
Okay, thank you.
Okay, questions? No?
Thank you.
Okay, now we have a next speaker. Ash Abdibastami from Australia. Metallurgical challenges and solutions in repair welding of chromium cobalt alloy steels. A case study on gas turbine starter rings.
Hi, everybody. Can you hear me?
Yes.
Hi, everybody. I really appreciate the opportunity to speak at International Conference on Welding and Related Technologies. My presentation will focus on challenges and solutions in repair welding of high alloy martensitic stainless steels, specifically a case study on a gas turbine stator ring made of chromium cobalt alloyed steel. Stainless steels are classified into 5 main categories based on their stable phases and microstructure and room temperature. So we've got austenitic, ferritic, martensitic, duplex, and precipitation hardening grades. These steels are mainly selected for their corrosion resistance due to their protective chromium oxide layers on their surface. Among all, martensitic grades are in high demand across various industries due to their corrosion resistance, high strength and hardness, as well as excellent wear resistance. so this makes them suitable for applications in various sectors such as power generation, oil and gas, petrochemicals, mining, etc. So they generally contain lower nickel levels than austenitic grades and are positions on the left side of the Scheffler diagram. In the iron chromium system, the high carbon content of martensitic stainless steels results in a wider gamma loop, meaning that carbon stabilizes austenite at high temperatures. So these grades have lower nickel content that allows ferrite to remain stable at room temperature. As a result, when austenite becomes stable at high temperature, it facilitates the formation of martensite, as the transformation requires austenite at elevated temperature and ferrite at ambient temperature. So quenching results in transformation of austenite into martensite, which is the basis for producing such grade of stainless steels. Repair welding of martensitic stainless steels, especially steel castings, is a cost-effective solution, reducing the need for expensive replacements and minimizing downtime with quick repairs, especially for a steel castings component. So it preserves the original design and promotes sustainability by reducing material waste. Additionally, it's versatile, making it suitable for various industries. These steels are highly prone to cold cracking after repair welding, which presents one of the main challenges. Two critical factors that contribute to cold cracking are microstructures susceptible to cracking and residual stress. When the carbon content increases and hardness exceeds 350 vickers, the microstructure becomes more prone to cracking, as is common in martensitic stainless steels. Besides the high residual stress generated during the repair welding, especially on cast parts with high levels of constraint, further promotes cracking. More importantly, if a source of hydrogen atoms is present, a specific type of cold crack known as hydrogen-induced cold crack can occur after repair welding. So in addition to hydrogen cold cracks, retained austenite formed due to incorrect preheat temperatures poses a significant risk in the repair welding of martensitic grades. So when the preheat temperature is set between the martensite start point and finish point temperatures, some austenite remains in the system. So as the steel is tempered and cooled during post-weld heat treatment for stress relief, the likelihood of retained austenite transforming into martensite increases, which can lead to either cracking or reduction in impact energy. So the appropriate preheat temperature should be set either below the finish point or above start point temperature of martensite. However, using a preheat temperature below a finish point is only suitable for thin sections, while for thick sections, the optimal preheat temperature is above start point temperature, known as Mart tempering cycle. So this case study focuses on repair welding of a stator ring that is a key component of one of the Siemens gas turbine, which is a heavy-duty industrial turbine used for mechanical drives and industrial power generation. The stator ring is made of chromium cobalt alloyed steel with a martensitic microstructure and was produced by investment casting process. So we found that casting defects such as cracks blowholes, shrinkage, and porosity are unavoidable in the casting process. So the reason is due to high alloy content and complex geometry of the ring. As a result, repair welding was selected as the best solution to repair defects. As shown here, in some instances, sections thicker than 1 inch required repair by building up filler metal to the area. So by adjusting the preheat temperature to a value higher than the martensite start point temperature, specifically set at 500 degrees Celsius, we applied a martempering temperature cycle technique. So this approach aimed to achieve temperature stability in the entire thickness of the material and prevent formation of retained austenite, which could be really detrimental during the tempering step. Besides, this preheat temperature combined with the subsequent post-weld heat treatment at 650 degrees Celsius for the purpose of tempering and stress relief of repaired area. And in another cycle, another temperature cycle, we used a preheat temperature of 200 degrees, which falls between the martensite start and finish point temperature. And the sharp PV notch impact energy were measured at room temperature for both heat-affected zone and weld metal. The results showed that when a lower preheat temperature for this grade of steel is used, something around 200 degrees Celsius is used, the impact energy value drops, indicating a transition from ductile to brittle behavior. However, by increasing the preheat temperature to 500 degrees, which is above start point temperature of martensite, an improvement in the impact energy values is observed. So this is correlated with a reduction in retained austenite formation, as mentioned previously. And the hardness profile measured across the repaired area was in acceptable range for the sample with higher preheat temperature. So to successfully perform repair welding on such chromium cobalt alloyed steels, it is necessary to consider several precautions to avoid failure, catastrophic failure. Selecting the proper preheat temperature and conducting a martempering cycle not only prevents hydrogen cold cracking, but also reduces the formation of retained austenite and improves impact energy after repair welding. So preheat temperature is in the range of 600 to 650, post-weld heat treatment is in the range of 600, 650, depending on thickness, also result in stress relief and minimize the risk of hydrogen cold cracks. And other precautions include using low hydrogen process, such as TIG welding, as well as austenitic filler metals to reduce the risk of cracks. Thank you, and I would like to acknowledge Weld Australia for giving me this opportunity to attend in this great conference. Thank you very much.
Thank you for interesting report. Please, question. Maybe colleagues in Kyiv. Okay. If no questions.
Hello, thank you for interesting talk. Just question, not directly to your results, but may you estimate the stresses and effect of preheating on residual stresses that arise in materials, new materials?
Sorry, I couldn't hear your questions. Is it possible to repeat it once again?
Do you have information how preheating different temperatures has influence on residual stresses on the materials that you investigate?
Oh, okay, so in terms of the residual stress, the main factors that contributes was the level of constraint on the area that we did repair on. So in terms of the temperature, of course, increasing the preheat temperature has a positive impact on reducing the residual stress. But the main and critical factor was constraint, and especially because these grade of steels have a very high yield strength, they have a very high level of residual stress after welding. So we didn't study the effect of preheat on residual stress, but it seems that increasing the preheat temperature from 200 degree to 500 degree, which is in the area of austenite, has a positive impact on reducing the residual stress as well.
Thank you. And again, another question. So you do repairing on very complex details, and they are used in severe conditions. So it must be tested a lot to get permission. So what are you going to do? Or do you implement your repair details in the real condition?
Yeah. In terms of in terms of the process to do the repair, we first did the procedure qualification record on test piece. So what we did, we simulated the actual condition on the test piece from that steel casting, and we followed the qualification standard of ISO 15614 for qualification of welding procedures. So after getting the result from that test piece, that is a kind of sort of simulation of that actual condition, we got the result, and once we passed the result, we did the welding on the actual part, and we implemented those procedures on more than 10 units that are currently in service.
Okay, thank you. More questions? If no, please send to us along.
Thank you very much.
Our next speaker, Alexey Kadlyak, laser synthesis of CBM containing abrasive ores.
Все? Не працює. Що? Okay. Dear colleagues, I would like to present our investigation, which named laser synthesis of big boron nitride contained abrasive layers. Next, please. Okay, in general, application of cubic boron nitride is good decision for manufacturing of abrasive tools, but in this case, we have some significant issues. First of all, holding force of grain by bonding materials is not enough to perform treatment with high quality and high productivity. Next position is low melting temperature of bonding material, make a limitation for processing of materials with variable specific properties. For another hand, it is hard to produce tools with low thickness and with high strength. And between bonding materials and cubic boron nitride grains could be chemical reaction if we use exciting methods. Next slide, please. To solve these issues, we should provide next steps. First of all, investigate influence of laser heating on strength of cubic boron grains. Next one, choose optimal technological schemes of laser sintering. Next one, choose appropriate materials to ensure a good bonding condition. And after that, investigate the process of laser sintering on free grains and on previously coated cubic boron trained grains. And investigate influence of laser sintering parameters on the properties of format composites. Next one. In general, all parameters of this process could be combined in three groups. First groups describes properties and condition of laser beam. Second one describes position of CBA grains and bonding material. And third one describes the condition of radiation and interaction of this position. Combination of all these parameters determine the characteristic of format layers, which on the next step determines the characteristic of format tools. Experimental investigation was provided using different marks of CBN grain. Part of this was previously covered by copper, nickel, and titanium. As well, different marks of bonding materials were used, and chemical composition of these materials are presented on bottom table. Next one. In investigation, we use two types of lasers. It was CO2 lasers with wavelength 10.6 micrometer. And second one, it was NDX lasers with wavelength 1.06 micrometers. The laser power was in range between 200 and 1000 watts. As well, the changed parameters was processing speed and diameter of laser beam, which was in gap between 2 and 6 millimeters. Part of samples was irradiated in atmosphere of air, and second part in protective atmosphere of argon. Okay. In experimental research was used two scheme of radiation. First scheme, it was direct radiation of CBN grains, and second schemes contains previously mixed between CBN grains and bonding materials. And in first case, we put grains on the graphite plate, irradiated these grains, and after that sent it to strength test. In the second case, this mixture, which was mentioned about, was input on steel plate, irradiated, and after that, for separation grains and bonding materials, was dissolved in acid mixture. After that, grains was also sent to strength test. Next, please. Okay. As a result, results of strength investigation, we have a situation that grains in each case of marks of cubic boron nitride, we have situation when treatment was under protective atmosphere, we have a bigger level of strength of grains. Here we should mention that compared to initial state of grains, we have a little bit lower level of strength, near 6 or 6-8%. But But initial state of these cubic boron nitride grains have the same equal of defected grains. That's why we can say that this decrease of strength could be explained by this defection of initial state of grains. Next, please. The set of experimental results give us possibility to separate recommended field of temperature parameters of treatment. And over these fields, CBN, VBN transformation have placed, and CBN and HBN transformation as well. Both of these transformation are unacceptable for processing of abrasive tooling. Next, please. Here we can see such kind of transformation depend on level of power of laser beam. On the picture A, we have the initial state of cubic boron nitride. On the level picture B, grains was irradiated by laser beam power 300 watts and the fixed condition of speed and beam diameter. And we don't have any unacceptable changes in grains. But when we increase the power of laser beam to 500 watts, we can see that some cracks have place on it. I have a mouse, no? Oh, here you have these cracks. Increasing beam power to level 800 watts initiates transformation CBN to HBN structure. Next, please. Okay. General analysis of all results in each cases of bonding material and each cases of CBN grains give us possibility to separate zone of optimal modes. And this of, next please. This optimal modes we can separate in both cases when we use CO2 laser and Nd:YAG laser. Next, please. Okay. If we discover treated area, we can see that in resulting we have some good mixture between base material and bonding material with partially immersion of cubic nitride grains. Here we see the green color is ferrum from base materials and blue color is copper from bonding materials. Next, please. And in general, we see the uniform the dispersion of including components of bonding and base materials in treated area. Next, please. Macro and micro photo can show us that we have partially immersion of CBN grains in treated area. Next, please. And it's good composition because in this case we have good good parameters of holding of grains and good treatment condition. Next, please. One more possibility to increase the property of our instrument, we can use some internal layer. Using of this layer could provide to decrease thermal load on base material and make the condition between base material, bonding material, and CBN grains better. Okay, next, please. As a conclusion, we can say that during our research, recommended technological parameters for laser investigation were established. It is recommended to use protective gas during the sintering process. It could increase resulting strength of grains. It is also advisable to use previously coated grains. It can decrease temperature load on the CBN grains, and the discussed laser sintering process essentially increase the productivity of process of producing the abrasive instrument using cubic boron nitride grains. Thank you for your attention.
Thank you for your report. Please, questions.
What kind of laser radiation do you recommend? Radiation with wavelengths 6 or
In general,
how its activity of your material depends.
In general, we can use both of these wavelengths, but when we use CO2 laser with a bigger level of wavelengths, it was more friendly, if I can say like that, friendly regime for cubic boron nitride. When we use shorter wavelengths, it was higher load on the cubic boron nitride, and in general, we should decrease the power. It can be explained by absorption of laser beam with different wavelengths. But in general, we can use both of types of wavelengths.
Because it's GTE.
Ну, хіба хочеш, мусиш.
Okay. We have a question.
Okay.
Good morning. Thank you for your presentation. And I have a question. Since you are operating at the temperature of 800 to 1400 degrees Celsius, is there any measurements of the depths of the penetration of the CBN grains inside of the base material you're using, as most of these materials have a melting point of 1000 to 1200 degrees Celsius, which is lower than the CBN grains?
Okay. In general case, CBN grains was on the top of format layer. And when we use previously coated CBN grains, they show the higher level of resistance of laser radiation, and as well as its high speed process that destruction of CBN grains didn't occur.
So the CBN grains remained at the topmost, as we used to call it, the skin layer, which is the first 100 micrometers of the material, yes?
We can input first layer, and in general, we can do multi-layer construction of our instruments. But in this case, will be some different starting condition for our treatment. If
Thank
I
you.
understand correctly your question.
Okay, more questions? If no, our next speaker is Anatoly Zavdaveyev. Mechanical properties of welded drawings of medium carbon alloy steels heated to temperature from 215 to 1200 Celsius degree. Anatoly, please.
Good morning, dear colleagues. Thank you very much for kind introduction. And just a second. Thank you very much for kind introduction. And today we are going to tell and to speak about mechanical properties of welded joints of medium carbon alloyed steels heated to temperatures from 250 degrees up to 1200 degrees. And it is well known that these kind of steels are classified as armor steels, and they are capable to withstanding significant dynamical loads and have a good wear resistance. And such steel can be used both for manufacture of military products subjected to impact loads and for the production of civilian machines and mechanisms. It is well known that most of these products are welded and with using of arc process. And this process involves local heating of welded steels to temperatures exceeding the tempering temperatures and reaching the temperature of 1200 degrees of Celsius. It should be noted that it is a very significant importance. The lowest tempering temperature, if we heated such kind of steels above such temperature, we can achieve undesirable changes in microstructure, and which could lead to such undesirable changes in mechanical properties. And exactly in this point, it should be mentioned very high attention while we using welding modes. And thus the purpose of this work was to determine the influence of welding modes on the heating and cooling conditions of metals in various sections of heat-affected zone. And let's consider more details the effect of arc welding and heated temperatures on hardness properties. Here we can see the hardness properties of welded joints made with conventional gas matter arc welding. And in this case, the cooling rate in heat-affected zone in the temperature range from 600 degrees to 500 degrees with 20 degrees of Celsius per second. And in this case, we can see very interesting dependence of hardness in welded joints. If we consider steel grade 71, this is high alloyed steel, Ukrainian manufacturing, and we can see that the properties are quite stable during wall welded joints. At the same time, the properties of international or foreign manufacturers of steel reveals very significant softening in softening zone. And further, we will see the conditions and why such effect occurs. And as in our real condition, we have predominantly foreign manufacturers of armor steels. And in this case, we should pay attention to choose correct welding modes to eliminate such effect of softening. Let's consider chemical compositions of investigated steels. And here should be noted and underlined the peculiarities of chemical compositions. For example, if we consider high stable steel grade 71, we can see that alloying system, especially with such elements as chromium and nickel, have very good level of alloying. And for foreign manufacturers of steel, we can observe that the alloying system is at lower value. And the hardness of such high hardness and high strength steels provided due to micro-alloying of boron. At the same time, the mechanical characteristics of these steels are very close. For example, we can see that the yield stress and optimal tensile stress almost at the same level, as well as plasticity and fracture toughness, obviously hardness. However, there is a very big difference in this steel during consequent welding procedure. Let's consider more close. Thermal kinetic diagrams of such steels. Here we present thermal kinetic diagram for steel grade 71 with good alloying system, and example for foreign manufacturing steel grade Reimer 500. And here we can see very interesting dependence or properties. In almost all, not almost, for steel grade 71, in all range of cooling rate, we have fully Martensic transformation in austenity. And while we can see the steel grade Reimer 500, we can see a mixture of phase transformation in range of the temperature between 600 and 500 degrees of Celsius. Here we can see the mixture of bainitic and martensic microstructure, and at high cooling rate temperatures, we can observe martensic transformation. This leads to the following changes in mechanical properties of considered steels. Here, it was the following experiment. The bulk sample of armor steels were simulated in a machine which provide fast cooling, fast heating and cooling rate in accordance with welding thermal cycle. And we have simulated different cooling rates in a range of the temperature between 600 and 500 degrees, and varying from 5 degrees per Celsius per second, 5 degrees of Celsius per second, up to 30 degrees of Celsius per second. And if we consider steel grade 71 with a high level of alloying system, we can see that beginning from 15 degrees of Celsius per second cooling rate, we already achieve the satisfactory mechanical properties. And very important to underline that the level of plasticity remains at a quite high level. If we consider the foreign manufacturer steel such as Reimer 500 or Armox 500, we can see a little bit different dependence. And for providing the needed mechanical characteristics, we also should start from the cooling rate temperature between 15 degrees of Celsius per second. And in this case, we achieve the following mechanical properties. Yield strength is up to 1,200 MPa, and ultimate tensile strength is up to 1,500 MPa. But in this case, we have significant degrees in plasticity characteristics, which is undesirable for welding joints of armor steels. The similar situation can be observed and also using Armox 500 grade steel. The next one, very important characteristics of mechanical properties is obviously impact toughness. And in this case, we have investigated different type of welded steels, different type of welding modes, and also we added different conditions of preheating. And if we provide preheating before welding, we can obviously govern this cooling rate in welding. In this case, we can see that from the beginning, the yellow bars is the base metal characteristics for Reimer 500, Armox 500, and steel 71 degree grade, sorry. And we can see the following dependence. For steel grade 71 and for steel grade RMAX 500, we have satisfactory level of mechanical properties. At the same time, for very low alloyed steel Raymar 500, at condition when we have high heat input welding mode, we have impact toughness below the minimal necessary level for such welded joints. And this effect is conditioned with alloying system. And for design of welded mods, we should pay attention, obviously, for alloying system and for transformation, structural and phase transformation, which is occurred while welding. As a consequence, we can state the following conclusions. For the welded joints of medium carbon alloyed steels of high hardness, it is typically formed areas with increased and decreased hardness in relation to the base metal. And depending on chemical composition of steels, the metal hardness in the hardened zone can increase by 5–10%, and in the tempering zone, it can decrease by 10 and 25%. And here I should underline that the better the alloying system, the less decreasing in softening zone of mechanical properties. And the more sound welded joints can be achieved. The next one is that regardless on cooling rate of the welded joints and the martensic structure, variant dispersion is formed in the overheating zone of heat-affected zone metal of steel grade 71. With the increase of cooling rate, it increases, and it's typically for heat-affected zone metal, for RMAX and Raymar steels, that exclusively martensic structure is formed in them to cooling rate exceeding 5 degrees of Celsius per second. And the last one is that increasing of cooling rate in the interval between 600 and 500 degrees of Celsius. Welded joints from 5 degrees of Celsius to 20 degrees of Celsius per second leads to an increase in the strength properties of the metal in the overheated area of the heat-affected zone by 12–15% and decrease in plasticity properties up to 35%.
Thank you for
Dear
interesting.
friends, thank you very much for attention, and I will be very glad to answer any questions.
Thank you for report and discussion.
Thank you for the presentation. My question about some other important factors, what's going on during preheating of these steels, carbon steels, middle carbon steels, only structure formations, nothing about hydrogen, for example.
Thank you very much for your question. Yes, this is very important question. And in our study, we made research in direction of preheating, actually for governing cooling rate in heat-affected zone. If we increase the preheating temperature, the cooling rate is decreased. And concerning hydrogen, yes, there is such investigation, but it wasn't the topic of current research. And it should be mentioned that in our case, it was used as a welding material, the high alloyed steel, grade 4–370 titanium. And such welding material is reveal very low susceptibility for hydrogen. We eliminate this problem using the special type of welded material.
Thank you.
Anatoly, thank you for a very interesting topic. Tell us, please, what steel grade would you choose to make this all the things you showed us?
Thank you very much. Also, very interesting and important question. Obviously, I choose the steel grade 71. However, in our reality, we should make decision also between foreign manufacturers. And in this case, I will advise obviously to use steel grade Armax 500. And this is because the stability of the properties of this steel is more high, and this is conditioned by, please see this table, by the more high level of nickel alloy. And this provides high stability of mechanical properties.
Thank you very much.
More questions?
One question on my side. Anatoly, please tell us which method do you use to join these materials?
Thank you, Sergey. Gas metal arc welding in the atmosphere of argon and carbon oxygen too.
Okay, thanks. And second last question. Which type of materials, additive materials, you used? Rods, buses, whatever.
Rods, not rods, steel plates.
Which chemical properties? It's middle carbon material. Or...
Here is the chemical properties of steel plates which were welded.
Okay, thanks.
More questions? No? Please thanks to 07.
Thank you very much. Thank you very much for kind attention.
Our next speaker, Vladislav Haskin, using spectral parameters of compressed arc plasma to develop basic approaches to smart welding.
Hello, ladies and gentlemen. My presentation was named using special parameters of compressed arc plasma to develop basic approach to smart welding. The relevance of the processed work of the proposed work lies in the study of the efficiency of laser plasma and laser plasma welding technologies. The analysis of the possibility of obtaining and applying information with the special composition of the arc energy source, as well as the creation of automatic welding monitoring system, take into account the peculiarities of investigation process. First part of my presentation, named evolution of the efficiency of energy transfer of a laser plasma heat source to metal during welding of carbon and stainless steel. In laser plasma welding, the synergetic effect manifests itself in a non-additive insertion in the area of same intersection. The effect can also affect the effectiveness of energy input into the weld pool. To test this hypothesis, a fertilizer with a power of up to 2 kilowatt was used. Так. Determining the efficiency of energy transfer during welding will alone evaluate the effectiveness of the welding process, determine the presence of a significant effect of in the case of comparing the values of the inductor of different process and cases of welding. The implementation of the synergetic effect in laser plasma welding occurs mainly due to hydrodynamic process in the welding pool. Next, please. Yes. The manifestation of the synergetic effect depends on the welding speed. With an increase in the welding speed, the effectiveness index of the hybrid process change from 1.2 to 2.25. Manifestation of the synergetic effect in laser plasma welding of carbon and stainless steel you can see in this slide. Second part on my presentation named using special parameters of composite arc plasma to develop basic approach to smart welding. For special studies, for spectral studies, spectrometer with CCD detector was used. Laboratory stand was created on this basic of this spectrometer. The instrumental circuit of the applied spectrometer was assisted using radiation from a low current near 5 milliampere low discharge plasma. Plasma spectral in the wavelength range of 650 up to 1000 nanometers of a high current welding arc, low with on arc CO2 mixture at arc current 100 ampere and 80 ampere. The values of the temperature of population of the electron levels of oxygen were 10,000, near 10,000 at composite arc current 100 ampere and near 7,000 at a current of 80 ampere. With an increase in the arc current by 20%, the concentration of charge in it increased by 1.5 times, which leads to increase in the arc temperature by 1.2 times. So part of my presentation named using an automatic monitoring system to automate the management of welding and 3D printing process. Welding arc monitoring system based on spectral analysis with stabilization energy input into the weld pool and eliminate the risk of incomplete fusion, fistulas, and burns through weld seams. To implement intelligent welding, it is a process to firstly it's introduce feedback into the welding system that takes the spectral composition of the welding arc plasma, and second create a self-learning system based on feedback and nuclear networks. And in the end of my presentation, it's conclusions. This energetic effect in yes, it's very speedy. This energetic effect in laser plasma welding of stainless steel is manifest in the growth of arc voltage by 1-3 volt compared to plasma welding, as well as in the increase of the energy absorbed by the metal by 6% relative to the sum of the individual effect of the components. The message spectra of the welding plasma are gradation in the wavelength range of 650 up to 1000 nanometers made it possible to calculate the extraction temperature of the main components of the spatial range of argon and oxygen with the framework of the location thermodynamical equilibrium model. And it was found that with an increase in the current of composed welding arc by 20%, there is an increase in the charge concentration in the arc plasma by 1.5 times and its temperature by 1.2 times. Based on the obtained results and new approach to the development of intelligent plasma welding process, it's proposed including the percent of feedback in the technological complex that tracks the spatial composition of the welding arc plasma. Thank you for your attention. Maybe who have questions?
Thank you for your report. Please, questions.
Alatonic Institute Welding. Thank you for interesting report. I have one question. What do you mean when you say intelligent control system?
Thank you for your question. One moment, please. I won't demonstrate it, my answer. 1 minute. Oh. Our intelligent welding system create a self-learning system based of feedback and nuclear works. Yes. One second.
Vladislav, one question concerns first part of your presentation. Please tell us what kind of laser did you use in laser arc welding?
We have fiber laser, power 2 kilowatt.
Wavelengths of laser beam. 1.07 nanometer, microns. Thanks.
Please.
Did you measure on the local values concentration and temperature of arc welding? Or what about distribution, radial distribution of this?
We see all plasma, don't local. It's about plasma surge complete. One moment, I demonstrate my answer. One moment, please. We have 3 spectral lines. In these lines, we see energy and electron energy and temperature, and we have one more, please, next, and we have a stand like this, and we see all plasma sources. Please.
Did you measure these parameters for arc plasma without laser beam?
Without. Only arc plasma. Only arc plasma, argon and CO2. Mixture argon and CO2.
Thank you.
Thank you.
More questions?
Maybe
No.
we have one more question.
Yes, please, question.
My name is Dmitry Kovalenko. Please confirm your conclusion that arc pressure and hydrodynamic flows are affecting on big penetration in the hybrid process.
We don't see hybrid process in measuring of temperature plasma, and we see hybrid process in welding. One more, please. Maybe is this just a second, please. Next slide. Maybe this. We see hybrid process and look this. We see very very high result of this process. My business.
Okay, more questions? No.
Thank you very much.
Okay, it's time for coffee break. Waiting for you here at 12 o'clock. Хорошо.
Да, там просто вот эти две опции сверху вылезли. Я уже думал, это не так я решил, Я на каске мне чуть не сломался. Я ношу. Я что, видите, ношу. Останешься, вернись. А, ну, все. Не, ну, а что, у второго чувака не работает? Я не знаю.
Я бы еще отсюда мышку убрал, если честно. А то они ее, вот те, кто с бумажкой, они ее постоянно где-то рукой дергают, и что-то происходит.
Блин, у нас, кстати, тут слышно.
Надо не видеть, вот там сидят. Ну, сегодня нет, ну, так что, надо проконсультироваться. Не стоит выключить перед приходом. Я думаю, что однозначно да.
То есть может будет переключаться. Ну, в крайнем случае, я тогда это самое.
Нет, с этого компьютера там оно 100 запущено. Тут не переключаешься, да, будете говорить, но вот она работает.
Право-влево.
Да. Это вперед, это надо.
Я понял.
Проверим, сломал свой тест. Не сломал.
Не, это работает, только указка не работает.
А, нет, да, тут на мониторе.
Не, ну да.
Dear colleagues, let's continue our conference. Next speaker, Sergei Maximov, the influence of the welding thermal cycle on the distribution of iron elements in the structure of the heat-affected zone of welded joint of duplex steel 2205.
Mr. Chairman, dear colleagues, I would like to represent some results of our investigation in the field of wet underwater welding for the duplex steel. It's known that today the quantity of the structures made from the duplex steel will become wider and wider. There are many constructions which work in the underwater condition. That is why it is necessary to have the tools that help as is necessary quickly and with necessary quality repair such structures. That is why we begin such investigations. In duplex stainless steel, the optimal combination of high strength characteristics and corrosion resistance, primarily against pitting corrosion, as well as stress corrosion cracking, is ensured by the ratio of ferrite and austenite phases in the weld metal as 1:1, it is 50% of each component. Under the influence of the thermal welding cycle, due to the effect of the high heating and cooling rates, the austenite ferrite phase balance is disturbed, which in turn affects the mechanical properties and corrosion resistance of welded joints. Diffusion of alloying elements in austenite and ferrite affects the formation of the microstructure and the distribution of the chemical elements in the material, which affects the mechanical properties, corrosion resistance, and other characteristics. Optimum distribution and concentration of alloying elements in each phase contribute to an increase in strength, crack resistance, and corrosion resistance of duplex steels. Almost no study in the literature on the distribution of the alloying elements and nitrogen in the austenite and ferrite phases at cooling rate different from the normal one, for example, during welding in the water environment. Therefore, the study aimed to determine the distribution of alloying elements and nitrogen in ferrite and austenite of different morphologies, as well as the delta gamma boundary in the heat affected zone, depending on the cooling rate during welding. The simulation of microstructures corresponding to those formed in the heat-affected zone under the influence of the welding thermal cycle was performed on Global setup according to the thermal procedure, heating at the rate of 100 degrees centigrade per second to a temperature 1300 degrees, holding the peak temperature for 2 seconds. During cooling of the samples, the welding thermal cycle corresponding to welding in air and vent underwater welding were simulated. After thermal simulation, samples were cut out for further studies using optical microscopy and analytical scanning electron microscopy. The content of austenite and ferrite in the simulated heat-affected zone was determined using the MIPER image analysis software. Electrolytic degradation was carried out in the ammonium sulfide solution at a voltage of 15 volts. Optical metallography was performed and versament at neophot microscopes. Microhundreds was measured in a LECO device. Scanning electron microscopy and energy dispersive spectroscopy was used to determine the distribution of alloy element and nitrogen using the scan mirror scanning electron microscope with Oxford instrument X-ray detector. The equivalent number of resistance to pitting corrosion was determined by the formula Pren equal weight percent of chromium plus 3.3 weight percent of molybdenum and 16 weight percent of nitrogen. The results of determination of The results of determination of distribution of alloying elements in the heat-affected zone microstructure between ferrite and austenite phase and the delta gamma boundary are shown in this table. We tested 4 samples. First samples is a weld made in air condition, and the samples was cut off the middle part of the weld. In this case, the cooling speed is equal 8.21 degrees per second. Sample number 2 is a weld made in underwater condition. Sample was cut off the middle part of the weld. In this case, the welding cooling speed is equal 81.70 degrees per second. Sample number 3, also made underwater and cut off of the beginning of the weld. In this case, the cooling rate is 165.85 degrees per second. And last one, also a weld made in the water condition and cut off near the crater of the weld. In this case, we have the maximum cooling speed equal 320.51 degrees per second. The following slides show the microstructure of the high temperature region of the heat affected zone, modeled with different cooling rates and marked areas in which local determinations of alloying elements were made in the ferrite and austenite phases and at the delta gamma boundary. In this slide, we can see the sample with the cooling rate in the temperature rate 1300 to 800 degrees centigrade equal 8.21 degrees per second, which correspond to weld in the air. Spectra number 1, 4, and 6 correspond to grains of delta ferrite, and spectra number 2 and 3, grain boundary austenite, spectra number 5 with Mattstetten austenite, 7 and 8, diamond-shaped austenite. The same spectra with different magnification are shown nearby. This slide shows a sample of the simulated thermal cycle corresponding to wet underwater welding with a cooling rate 81.70 degrees per second. Spectra number 1 and 5 correspond to grain of reformed delta ferrite, which will be formed as a result of 2 opposite processes: the dissolution of primary austenite grains during heating up to 1300 degrees, and then already upon cooling, new grains of reformed delta ferrite were formed. This is confirmed by relatively high values of austenite forming elements, nickel and nitrogen, spectrum number 1. In spectrum number 5, there is also an increase in the value of austenite forming elements. It is in these grains of delta ferrite due to the high cooling rate and inability of fully redistribute alloying elements between austenite and delta ferrite, then chromium to nitrogen may precipitate in the future due to the increase in austenite forming elements in the grains of delta ferrite, primarily due to supersaturation of the nitrogen. If we compare spectrum number 3, there is an increase of ferrite forming elements, chromium, compared to its content in the base metal, and molybdenum compared to its content in the base metal, and a decrease in austenite forming elements, nitrogen in base metal and nickel. The largest amounts of austenite forming elements, especially nitrogen, are offset in the delta gamma boundary up to 0.98 weight person, spectrum number 4, and 0.83 weight person, spectrum number 6. This slide shows the microstructure modeled with a cooling rate 165.85 degrees per second, which corresponds to the thermal cycle during the wet welding, the beginning of the weld, with marked area in which local determinations of alloying elements were made and a sample corresponding to the cooling rate, 320 degrees per second at the right near the weld crater. For comparison, the microstructure of the base metal is shown in the lower part of the slide. The same trend as described above is observed here. If the austenite grains and near the delta gamma boundary, there is an increase in austenite forming elements, especially nitrogen, spectrum number 3, 4, and 5 in the left figure, and spectra 3 and 4 at the right figure. The highest value of the nitrogen 0.73 weight percent is observed in the delta gamma boundary sample of the left and spectrum 3 sample of the right. Content of the nitrogen near the 0.62%. As in previous samples, the grains of reformed delta ferrite have an increased content of nickel and nitrogen in the same sample of the left figure. The same regularity was found as a maximum cooling rate also. The largest value of PREN are on the delta gamma boundary, second sample, and equal to the 48.69. The nitrogen content is 0.98%, and in the PET sample, PREN is equal 41.69, and the quantity of the nitrogen 0.83, as well as in the austenite phase sample, and is 41.26, while the nitrogen content is 0.73 weight percent. And in PREN austenite sample 3 is 41.81, the nitrogen content is 0.73%. The value of PREN delta ferrite in all samples is lower than in the austenite phase and is in the range from the 30.6 to 38.40. This emphasizes that it is due to the diffusion of alloying elements, primarily nitrogen, to the difference in PREN values of the phases decreases as the time spent in the temperature end of phase transformation decreases. The highest microstructure value is in the range from 3,300 up to 5,150 MPa, was found in the both Wittgenstein and grain boundary austenite in the high temperature heat affected zone. A decrease in the microhardness of austenite occurs with the increase in the cooling rate from the 8.21 to 320.51 degrees per second, and is in the range of the 3,360 and 4,390 MPa. The microhardness of austenite in base metal is mainly 2,097 up to 3,090 MPa. Something reach the 3,300, 3,570 MPa. A change in the microhardness of austenite may indicate that the main element influencing the microhardness of austenite is nitrogen. Microhardness depends on the contact of the austenite in the lattice. The nitrogen content in austenite ranges from 0.40 weight percent to 0.98%. The microhardness of ferrite does not change depending on the cooling rate and is equal to 2,300, 2,900. The microhardness of ferrite in the base metal is almost the same, 2,300, 2,570 MPa. The most significant variation from average value in base metal, according to certificate data, are observed for molybdenum, especially in its distribution in delta ferrite. Namely, then welding in the air, the range is from 3.16, 3.26 weight percent, to underwater welding in the middle part from 2.12 7 up to 3.49%. Beginning of the world, 2.57, 2.82%, and in the world, near the world crater, 2.42 up to 3.68%. The increase in the range in world crater can be explained by grain refinement at a high cooling rate. As for nitrogen, its content in austenite varies in the following ranges. Sample number 1, range 0.34, 0.73%. Sample number 2, 0.83, 0.98%. The grain boundary, near the grain boundary delta gamma ferrite. For sample 3, 0.29, 64%, and for sample number 4, 0.53, 0.62%. Thus, we can make the following conclusions. The effect of cooling rate on the distribution of alone elements in the ferrite and austenite phases in the simulated heat-affected zone of a 2205 duplex steel was studied under different thermal welding cycles using Global 3800. Our study revealed that the distribution of alloy elements between the austenite and ferrite phases is influenced by the cooling rate, particularly the time spent in the temperature end of phase transformation. Notably, an increase in cooling rate to 320.51% degrees per second led to a decrease in the difference in the distribution of alloy elements between the phases. Austenite of different morphology differs in the magnitude of the microhardness values. A change in the microhardness of austenite in different morphologies can result from the content of different amounts of alloy elements, primarily nitrogen in the austenite lattice. At the same time, the microhardness of ferrite does not change depending on the cooling rate. It remains almost constant both in the high temperature heat-affected zone in the range of a temperature 1300 up to 800 degrees. And it's in the low temperature heat-affected zone in the temperature range 800 to 500 degrees and is equal to the microhardness of ferrite in the base metal. The nitrogen content in austenite is from 0.40 up to 0.98%. A decrease in the microhardness of austenite in the high temperature heat-affected zone occurs with an increase in the cooling time rate from the 8.21 degrees per second up to 320.51 degrees per second, and is in the range of the 3,360, 4,390 MPa. The microhardness of austenite in base metal is mainly 2,970, 3,090 MPa, something reaching the value of 3,300, 3,570 MPa. Our findings suggest that the microhardness of austenite is primarily influenced by the nitrogen content in the austenite lattice. This is evident from the highest microhardness value observed for austenite in the high temperature heat-affected zone, both with Machtstetten and grain boundary austenite, which range from the 3,300 up to 5,150 MPa. The prime value of delta ferrite in all samples below is the austenite phase and ranges from 30.6 to 38.40. This means that due to the diffusion of alloy elements, especially nitrogen, the difference in the prime values of the phases changes as the time spent in the temperature range on phase transformation changes. Thank you for your attention.
Thank you for your report. Please, questions? questions? Maybe colleagues in Kiev? No. Our next speaker is Oleg Makhnenko. Calculation, prediction of welding distortion of large-sized cylindrical structures. Please, Oleg.
Thank you. Are you hearing me?
Yeah.
I would like to make a presentation, a calculation prediction of welding distortions of large-size cylindrical structures. The calculation prediction of large-size welded structures is still a complex problem because using the general software pockets, commercial pockets of finite element analysis requires a great power, computational power, and too long time of calculations for this problem, for solving this problem. That's why in our work we to predict distortions of large cylindrical structures such as pressure vessels or propellant tanks, we used the combined use of general methods of thermoplasticity and approximate method of inherent strain. The method of inherent strain allows to calculate, to predict the general welding distortions by methods of elastic theory. And in this slide, you can see that how to maybe presented the tensor of strain function, inherent strain functions in form of tensor of plastic strains. If the main directions of transverse and longitudinal directions of weld joint, the tensor of inherent strain function may be simplified, and only two parameters, the transverse and longitudinal shrinkage of welded shrinkage of weld joint, define this tensor. And this method of inherent strain functions assumed that the Hooke's law in the elasticity assumptions of this problem may be presented in such way, and you can see that in general form of Hooke's law presented in the right side presented the shrinkage functions as additional welded deformations. And in result, by the means of thermoplasticity analysis, on on the base of the using the simplified models, we can to obtain the parameters of inherent strain functions, plastic strains, welded plastic strains in the welded zone. For example, for longitudinal welds, by means of the three-dimensional model of a butt joint of limited size, and for circumferential welded joints, by using the simplified two-dimensional model of a butt circumferential joints with assumption of fast moving heating source and hypothesis of plane strains. In such way, first of all, by using the thermoplasticity analysis and such simplified model, we can obtain the parameters of inherent strains functions, and then by methods of inherent strain, we can predict the overall distortions of large size structure, welded structures such as cylindrical vessels or propellant tanks. In this slide, you can see the results of validation of method of inherent strength in comparison with general method of thermoelastic plastic analysis. For such structure, cylindrical shell with longitudinal weld of limited length, were defined or obtained the calculation results by two methods, thermoelastic plastic analysis and inherent strain methods. And you can see on these figures that results of defined by inherent strain method is too close to the more accuracy results obtained by thermal elastic plastic analysis. For demonstration, the ability of the method of the proposed method, we define the general welded distortions of the large size cylindrical vessel with diameter of 3.5 meters, thickness of the wall 10 millimeters, with length approximately 12 meters, and made from high strength aluminum alloy 2219. And in this slice, first of all, we define the parameters of inherent strength function, and we compare the results of inherent strength function for this material and for this thickness for two different welding process. First of all, more traditional arc welding and more new welding process, the friction stir welding. And you can see that shrinkage, welded shrinkage, or parameters of inherent strength function, and or distribution of residual plastic strains in the weld zone for arc welding are approximately 3 and more times higher, in comparison with friction stir welding. This is results of distributions of residual plastic strains for transverse directions, and this is for longitudinal directions. And then these results of inherent strength parameters were used for prediction of overall distortions of cylindrical shell on by method of inherent strength on at different stages of assembly welding of this structure. Now, first of all, first step of welding, this is welding of the longitudinal joint of one shell circle. And you can see that distribution of distortions or displacements in the shell has a complex character, and in comparison with arc welding with friction stir welding, we define that these distortions approximately 3 and more times are lower. This is radial deflections, and this is axial deflection in along axis of cylindrical shell. Next step is circumferential joint of two shell circles, and you can see that at this step the welding distortions also for friction stir welding are lower than for arc welding. And finally, the results of overall distortions for whole welded the cylindrical vessel with six shell circles and two bottoms. And also the distribution of distortions have a very complex character. In zone of weld joints, we have radial deflections at the neck, any distance from this welds, the shell is have positive deflections. Also, cylindrical structures has overall shrinkage, and also the distortions for friction stir welding is more low than for arc welding. In addition, I can say that for engineering use, we developed the software which allows to quickly define the very large complex of information concerning the distortions of large sizes cylindrical shells, welded shells, and also for informations for local plastic strains and distortions and residual strains, residual stresses in the zone of longitudinal, circumferential welded joints of cylindrical shells. And short conclusions. The mathematical models and calculation algorithm for operative numerical determination of welding strengths of large-size cylindrical shells with a number of circumferential and longitudinal welded joints have been developed based on the inherent strength methods. The inherent strengths of welded joints of cylindrical shell, plastic strengths in the axial and circumferential directions, can be determined by thermoplasticity analysis on simplified models of longitudinal and circumferential welding joints. The developed specialized software can be effectively used for in-process prediction of a stress-strain states in assembly welding of large cylindrical vessels. Thank you for your attention.
Thank you for your report. Please, questions.
Okay, I have a question.
Please. Please.
Thank you for your presentation, Oleg. As far as I understand, you compare the results of mathematical simulations under using the two models. Did you compare the simulation results with experimental real results?
In our, you understand that experimental results for large size welded structure is difficult to get, and that's why this is our study was in general was theoretical, but on the stage of defining the local residual stresses and residual plastic stresses, we conducted the experimental investigations, and we measured the residual plastic strength and residual stresses at in welded joints in butt welded joints of aluminum alloy 2219, and we compared the measured experimental data with obtained with our calculated data, and we have a good agreement. But in percent, no, the maximum in comparison of residual stresses, the maximum mistake errors was approximately 20%, but taking into account that very complex distribution of residual stresses in the this is was a good, I think it was a good agreement, and a comparison of experimental and calculation results allows us to modify our model and take into account in calculation the effect of softening of aluminum in weld zone, and this effect is very important for calculation of residual stresses.
Thank you.
More questions?
Thank you for your interesting presentation.
Sorry, we have one more question.
Ви використали функції усадки,
Okay, please.
на першому слайді.
As I understand from the first slide, you used the shrinkage function.
Чому було використано функцію усадки тільки в окружному та осьовому напрямку, а в радіальному ні?
Why didn't you use this function in the radial direction? Just used it in the circumferential and longitudinal.
We make assumptions that the main directions of our model is longitudinal and transverse directions with equals with directions of longitudinal circumferential directions of weld joints in cylindrical shells. And these assumptions allows us to make all another components of tensors equals to 0, and we have only three in tensor. We have only three component, and longitude axis and radial and circumferential, and third component, the radial, is equals the sum of these two components with negative.
В радіальному напрямку вона нехтовно мала. В
In
порівнянні
the
з тими.
radial direction, it's negligibly small.
Ні, вона не тут. In radial directions, in radial directions, the plastic strength, inherent strength is small. You are right. Is small, and but mathematically we can to define this third component by sum of in the principle of safe of plastic strength equals to two components of another two components.
Thank you.
One more question, please. Last.
З яких експериментальних даних ви отримували значення пунктів відсотків? Треба задавати.
And where did you get from what experimental data did you get this shrinkage function? It has to be assigned.
We investigated the experimental samples of butt joints of this material and welded by this technology. But on these samples, we investigated first of all the residual stresses, and and compared with calculation results. But if we have good agreement with residual stresses, we concluded that also we have a good agreement in calculation of plastic strains. Only such.
Thank you. Thank you. That's
One
all.
question.
Thank you for your presentation. I have a very short question about the dimension of the shell. What is the radius of this cylindrical shell, and what is the characteristic? You showed the value of displacement, but what is the value of deformation? Thank you.
In our example of cylindrical shell, the diameter of shell was 3.5 meters. It's enough large cylindrical shell, and length approximately 12 meters, and deformations, but deformations not very high, approximately near less than 10 millimeters. But for modern welded structures and such accuracy is normal, and such results is real. Such such level of deformation is real. Thank you.
Okay, please send to also one more. Our next speaker, Alexander Romanenko, current state and prospects for development in the field of welding of biological tissues with high frequency power sources.
Hello, everyone. Thank you for introduction. I want to make you more familiar with live tissue welding. I will give you general overview what is live tissue welding, what is the market, what are our competitors, what we do, what we manufacture, what researches we do. It works good. Well, method of high frequency live tissue welding was developed in Patton Welding Institute under supervision of Boris Patton, academician. And it was created in cooperation with few medical organizations. In fact, it was launched in 2002. Now there are more than 200 surgical procedures implemented in the practice, and approximately 40,000 surgery operations are being made annually. We have about 250 generators on the market, and about 100 hospitals use this technology. Other applications of live tissue welding is often used in abdominal surgery, in traumatology, pulmonology, gynecology, vascular surgery, and other applications. It's very good. This method provides following advantages for surgeons. I will mention just reduction of duration of operations by 20-50%, reduction of blood losses by 60-85%. Then for patients, it's very important the shortening the period of rehabilitation, and for hospital also. It will be reductions of stay of the patients in the hospital and cost reduction also. Well, some news about the market. I got this data recently. The market is not too big. Okay, oh, thank you. As for general electrosurgery market, it means generators and instruments. The growth is about 6.5% annually, and we will have the total market of about $9 billion in 2029. As concerning generators, help, next slide. As for electrosurgical generators, the trend is more speedy. It is about 8.2% annually, and then the market will be double in 2032, and it will reach $5 billion. Yeah. Well, as for consumption of these devices by regions, of course, North America is #1. about 40% of the market, and Europe is following them. What about the growth reasons? In US, they mentioned that they have a growing number of surgery operations, including cosmetic surgeries. That's why this method is applicated very oftenly and have great prospects. As for applications, popular method of welding is more popular, and the main consumers of the generators are hospitals and ambulatory surgical centers. That is very interesting slide. In what spheres of surgery or medical spheres generators are using? We have three big whales here. Is optical, ophthalmology, dermatology, and dental. It was a little bit surprise for me because our main partners are in another spheres of medical surgery. Well, we have a lot of competitors. Among them, it's world leaders like Medtronic, Eticon, Bova Medical, and they invest a lot of money into development of their devices. And there is estimation that Medtronic occupy about 30% of the market. Well, that is some examples of competitors' product. They have very good design. Usually the frequency of welding between 350 kilohertz and 1 megahertz. The power is from 10 watts to 400 watts. Generally, they do two kinds of operation. It's welding and cutting of the tissue. If we talk about the price, there are three segments: econom, from $2,000 to $10,000 professional, from $10,000 to $30,000, and premium from $15,000 to $50,000. But the price is going down because of high competition. And if we try to position our products, so it's like professional quality for econom price. A little bit about history and recent results. A little bit shorten this part. Just mentioned that for 30 years we developed a lot of devices, and we'll present the last models. It's EKBZ300, and the second model, the working frequency is 440 kilohertz, maximum output power 300 watts. We have a certificate. This device is included into state medical equipment register. What is the difference between these two devices? Of course, this device allows to make cutting, welding, and automatic welding. And the new model is switching more to automatic welding. The main idea is to place a special chip inside the instrument, and when you will connect this instrument to generator understand what is application of this instrument and will adjust parameter for welding. Well, it's another our device, ABI 3501. It's the application for irreversible electroporation for fighting of malignant tumors. The core idea is to locate tumor, and with a special instrument, to destroy this tumor, and later on the remainings of tumor will be deleted from the body by internal forces, let's say. I want to emphasize about the big power of this device. In peak, it reaches 100 kilowatts. And the maximum voltage for this device is 2000 watts. Of course, you can understand that it's just in peaks, in impulse. And of course, this generator is just a part of big complex of for surgery, because it is necessary to have special instruments and also special devices to locate the tumor before you start the operation. Well, also our specialists developed a lot of electrosurgical instruments for various applications. The recent results. Well, it's rather famous, the blood vessel closing as a numerical result. As for the strength of this connection, I just want to mention about 1,000 millimeters hydrardium. It corresponds to 7 times more than usual systolic pressure, blood pressure. Well, just a few days ago, I received these pictures from Filatov Institute of Eye Diseases. We have tight cooperation with them. And here it is a retina attachment to HORIT with a high frequency welding. Here we have a problem. I don't know, maybe mechanically there was a detachment of retina. And in this way, we see how the specialists treat this problem. Well, again, ophthalmology, it's tumor removal here. First line, the first picture and second picture. And also I placed here some instruments which are used in ophthalmology for high frequency welding. Well, also very recent results of intestinal anastomosis, and they call it end-to-end anastomosis. We manufacture special laboratory, of course it is laboratory instruments, special stand. We have a measuring system, both by water column and special devices. And we received one-time anastomosis results with which is approximately 6 to 9 times more strong than traditional Stapler's method. Well, welding of tendons, it's rather new. We do not reach here too high results, only 2 kilos. Strength, it's not enough for real operations, but we are working on this matter. Well, there are a lot of other applications, tumor removal, lung resections, also very interesting results in stomach bleeding treatment, welding of nerves, surgery on liver, ablation of head tissue, and other. Now we quickly go to prospects. As for our opinion, there will be useful usage of hybrid welding technologies when we will influence the tissue with high frequency electromagnetic energy, ultrasonic energy, mechanical and infrared energy. That is our plan. Also, we have to develop new tools for surgical intervention, and also new direction. It's development of new portable generators. which allow to work without external power supply and to apply them, for example, in military conditions or somewhere in the field for emergency medicine and veterinary medicine. Some conclusions. Market is growing. Our generators fill the world requirements. And new technologies, of course, can replace traditional surgical methods. And our engineers are ready to create new surgical devices by contracts. Thank you for attention. Glory for you.
Thank you for interesting report. Please questions.
Thank you for your presentation. What about new steps in production of instruments?
Well, for example, as for the recent request, we have agreement to meet these days with specialist of Filatov Eye Disease Institute in order to create some new instruments. It's like today requirement. Production, it's
not development, experimental.
I see. Probably Mr. Krivtsov knows that we are cooperating in production with one company only. It's Aleph company. It's, we'll see.
Okay, the question is, can your technology be applied to skin?
I know that before there were trial to weld skin, but specialists made some problems, and at the moment I cannot answer positively the question.
Okay, thank you. And the next question is, your shows market capacity, and you told that the most market is the United States market. What about the China and Europe?
Also, there was no data about specifically China, but it was data about
Global East.
Asia Pacific region or something like this. I will show you. Yeah, Asia Pacific region, it's 20% of the market.
Good. Thank you. Thank you.
No more questions? Okay. So, dear colleagues, we completed the first part of our today program, waiting for you after lunch on the second half.
Да, я сейчас
Микрофон выключать надо, да, когда он... Когда он не нужен, лучше выключать.
Ну, наверное, что поперечный не видно. На запасных нету с собой. Там что-то вроде было, непонятно.
Я вижу, как
Кстати, не просто такие, у меня батарейки с собой были, но она не садится, она работает, то есть это ты не не показываешь. Если ты чем-то по-другому показываешь, то видно, не
это надо подсадить.
Сладкий.
Прямо на экран надо подсадить, да? Вот это интерактивный экран. Это что, интерактивный экран? Подойдет?
Хорошо, да?
Нет. Сейчас молодые просто. Вот, надо для цель.
Так, если не это что только нормально. Я Забирайся, це можеш не виспати. Вот бачиш, що як ми з ним виспалися, що він піднімає, тому що где-то не просто.
Ну, пока не достаточно дешевле.
Я обычно не нервничаю, но что-то не так. Ты тоже вечером заснуть не нечего, то есть если блюдо надо лечь. Нет. Да мне что-то вообще какой-то кошмар, каждый вечер. Я уже думал, ничего не буду. Как раньше принято было. Это да, у нас информация. Не включили больше не было. А потом все на ближе, проверяй правильно, это наверное. Это, конечно, да. Да. Ну, поедем на канализацию теперь. Опять или полетим? Да, это выступил. Я не послушал. Время не поверил. Я выступил, что мне потому что это не видно. А я там понятно не А смотри, это будет, получается, туда поехали, банкет с интервьюем разводить, мы будем снимать, у меня будет партия людей, которые видите, я, я просто дилемма. Я тебя точно не спросил, я не хочу, чтобы они тебя опять мечтали. Я не запрещаю, что ты. Да. Я хотел фотографии, где-то встречали колбасы выходят. Да. Вы не перепутаете. Меня зовут Михаил. Ну, в таком случае, что отменяете? Грамотный сертификат. Може, лист, не знаю, може це електронний сертифікат, де ну, ти говориш про деньги, що додаєте за свої кінця. Екзамен.
Нам кнопка вперед назад. Та яка вперед, яка назад, щоб не було, як вчора там тупили. Все.
Почему?
Но у меня, наверное, должно быть чуть-чуть дальше. Там должна быть задержка на несколько минуты, наверное, задержка. Ну да.
Dear colleagues, let's start our will. I hope all of us have a nice lunchtime and we can start with the energy. So, here we go. Our first speaker is Dr. Alexey Kovalevsky, the Israel Institute of Materials Manufacturing Technologies, Haifa, Israel. Presentation named Laser Welding using Dynamic Beam Shape Technology and Practical Applications. I invite speaker to start the presentation, please.
Okay, hello everyone. Can you hear me? Can you see me?
Yes, we are here. You.
Okay, nice. So first of all, thank you for the invitation for this very nice conference, and personally, thanks for Dr. Sergey Schwab for first message, link, and invitation. And let's start. So now I'll try to share my screen. Okay, can you see a presentation? You have to see technical background, application of lasers.
Yes,
Yes, and now it's a topic, yeah?
Yes,
Okay, great. So today we'll talk a little bit about laser welding using dynamic beam shape, technology, and applications. So the theoretical groundwork for laser was laid in early 20th century with the development of quantum mechanics, and the concept of stimulated emission were proposed no one else but Albert Einstein in 1917. So the first practical demonstration of laser, which by the way is acronym, and it's mean light amplification by stimulated emission radiation. Can you hear me?
Yes.
Okay. Okay, some delay. So at the moment, looking ahead, the future of laser technology appears very promising with ongoing research into innovative laser sources, such as fiber lasers, ultra-fast lasers, quantum cascade lasers, and other femtoseconds lasers, and so on. And nowadays, this laser is used everywhere in every area of our life. Among them, of course, welding and cutting, medical applications, communication, laser printing, laser scanning, spectroscopy, and so on. But for us, very interesting thing is, of course, welding. So what is this laser, basically? So laser welding uses a powerful and focused beam of light with a very high density, approximately 10 million watt per square centimeter, to melt and join material together. The laser beam is generated by a special device and directed to spot and materials which need to be joined. And when the laser beam hits the material, it heats up really quickly, causing to melt. This melted material then solidifies to create a strong and precise weld. It's commonly used in industries where accuracy and speed are really crucial, like manufacturing and electronics. So typical laser welding process looks like this. We can see a beam which going through the metal and just melt the material. And we have any problems during stainless steel, for example, but when we go to some copper or some materials with a big reflection coefficient like aluminum or copper or something like this, we can see explosion and spattering of metal, and of course a lot of different defects, which is our main problem during welding. Usually, at the moment, scientists can distinguish two types of modes for laser welding. It's a conduction mode and keyhole mode. These modes refer to the different ways in which the laser energy interacts with the materials being welded. So in conduction mode, laser energy is absorbed by the material surface and conducts through the material. And the heat generated at the surface causes the material to heat up, melt, and form a little weld pool. This mode usually suitable for different thin materials and application where little penetration required. And the other mode is the keyhole mode, also known as deep penetration mode. And in this mode, the laser energy is intended to create a deep vapor-filled cavity called keyhole within the material. And this keyhole is surrounded with a molten material. This mode characterized by deep penetration into material. It can reach even tens of centimeters. It depends on power of laser. And when our parameters or welding parameters isn't good enough, there is a process which called the collapse of keyhole, which occurs to keyhole collapse and different problems. Okay. Okay, so this is our typical pore formation mechanism. And other defects like cracks, lack of fusion, and some other types of defects. So pore formation occurs when gases from the air, moisture, or even materials being welded release and get stuck in a molten metal. Another reason is the dynamics of the weld pool plays important way in gas entrapment. If the weld pool is not well controlled and there is a turbulence or instability, gases may be pulled into the molten material. So there is So there is two natural way to decrease the porosity. Is increase welding speed or use wobbling technique. What is wobbling technique? During wobbling welding, the laser or welding beam moves in a periodic pattern, creating back pressure, and it's going just like some feature or aid or internal or some other way. So 15 years ago, scientists start to understand that this is a way to decrease porosity and other type of defects. And one of the way was using beam shape. In our lab, we have such modern laser complex using OPA technology. When we have a single mode laser with a Gaussian beam and dynamic beam shape technology based on OPA technology. What does it mean? It's the optical phase arrays technology, which means that we have 32 different lasers which go in one fiber. After this, it's divided in a lot of different little lasers with power of 500 watts. And by the way of multipass filters, it's one more time combined into one beam shape. What does it mean? So if in case of regular laser, we use spot like this, using our lasers, we can just draw beam shape what we really want. It's depend. For example, this I called Mickey Mouse, and this is the clown, banana, line, and so on and so on and so on. So because of this, we can control form of beam shape, which allow a lot of different interesting things. One more time, we can draw the beam shape of laser with a frequency of 1000 kilohertz up to 10 megahertz. So it means that this beam shape is drawing probably 1 million times per 1 second. So this way we get a beam shape technology. Okay, I'm sorry for music. This is our presentation of our welding lab in Technion, Haifa. We have 6 axis position system and a single mode dynamic beam shape laser with coherent beam technology. Focal length is 800 millimeter and allow weld different tips. And configurable parameters are beam spot size, shape, focal distance, and power modulation. This is different examples of our welds. Okay, yeah, one more time. Wavelength 1000 nanometers, 14 kilowatt. That is quite big for penetrate several centimeters of steel and some other parameters. Okay, and today I'll briefly talk about several of our cases. Is welding of aluminum 6061, aluminum 7075, ultra high hardness steel, and 2 types of dissimilar types of welding, aluminum plus copper and inward plus titanium welding. It's just brief description of several our cases which we got last 2 years. So our base investigation was about aluminum 6061 because it's a very popular and famous wrought alloy which used in almost all type of industries, from automotive, aircraft, construction, food industry, and really different type of industries. According to chemical composition, 95% is aluminum, and we have a little addition from magnesium, chromium, manganese, silicon, just to stabilize the alloy. So we started our work from bead plate welding, and after this going to butt welding. And our main goal was go through conventional laser welding with speed of 50, 100 millimeter per second. We wanted to increase it up to 150 or even 250 millimeter per second. So you mean it's like 20 centimeters per 1 second. This is our welding speed without welding wire. That was the main challenge, to weld it without any additional material, any filler, any rods, just as is, just to connect to plates and weld it. So parameters that we take into account were laser power, welding speed, focal distance, properties of welding material, wavelengths, pulse rate, surface preparation, shielding gas, argon use, beam quality and diameter. And it was not enough for us. We also used dynamic beam shape, like one more parameters. So more than enough parameters we used for this investigation. So as I said, we started on bead on plate trials. We welded different frequencies with different beam shapes to propose understand impact of beam shapes and frequencies on the weld beam, and mainly on defects and heat affected zone and other materials properties. So we can see that there is a very big impact of frequencies on welded material. So for example, we can see that with the frequency 1 kilohertz, it's even without frequencies, we have some lack of fusion in a root zone, not enough penetration. And for 400 kilohertz, we have awful porosity during all the weld. And we can see that this was formed like banana with 1 point. The opposite of this beam shape was point and a line of banana. So here we can see that our defects are more concentrate, like cylinder, and here we have like spherical porosities. So it's quite interesting that we can understand that beam shape can really impact on form of defects. Other interesting things that we conclude was that for every beam shape, we can some no defect zone with the best of results. We have some maximum with good results and some minimum with poor, cracks, and so on. So it means that for every beam shape, there is a specific diapason range of frequencies, which can weld without any problems. So, but when we go to butt welding, we can see still a lot of problems. We started to understand why, of course, and we figure out that just with heat input over 45 joule per millimeter, it was required tensile and quite good performance of weld seam. Another very important options that we conclude was, by the way, it's most interesting probably things of all of this investigation, because all previous scientists said that if we have more turbulence, if we have more wobbling, we have more vibration and gases can just fill out our welding pool. But we can conclude after the investigation that for high turbulence beam shape like banana, infinity, or spiral, we have a very bad welding joint. There are other types of beam shape like medium turbulent shapes like circle or this several type of point. We have not good and not bad welding seams. That looks good, but mechanical properties were not so high. And for low turbulent shapes, like several dots or line, we got the best results. So why it occurs? I guess it's because of castability of aluminum. For high temperature, when it smells like 660 degrees Celsius, it's very fluent, it's very liquid, and because of this, just keyhole collapsed a lot of time for high turbulence shape, and we have to use low turbulent shape, close to regular welding. So this is several results of our investigation. So this was welding with 7 kilowatt with a beam shape of line. Frequency was 1000 kilohertz. Feed rate 150 millimeter per second. And tensile that we got was 228 megapascal. And tensile of base materials is 290 megapascal. So we almost got 80% of base metal without any filler, without rod, without any filler, just raw welding. Another type of weld will be a little bit increased feed rate. It was 190 millimeter per second and 9 kilowatt. We also got very nice results, 220 megapascal according to tensile tests. Yes, and bending results also was quite good. I also can say that we use a little bit defocus of probably 2 millimeter under the surface of weld. And so this is the way how we got these net results. So when we started to understand impact of beam shape on heat affected zone, we just understand that there is some type of impact, but it's not really important because, for example, for line, our heat affected zone was 80 micron. This is very, very narrow. And for some other type like Mickey or Big Cycle, it was 130, 140 microns. So it's a little big than a line, but it's still very, 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 very narrow heat affected zone. 100 microns. So because of this, we got such nice joint without any problems. Other case which I want to share with you today was aluminum 7075. So aluminum 7 is a very problematic type of aluminum. It's called now even in our books unweldable material because of high percentage of zinc, which is make it very prone to cracking. Another problem is porosity because of absorbing hydrogen gas. So this is a typical defects during the welding. It was some collaboration with the University of Stuttgart, and we tried to find a very narrow gap of 4 meters in which it was no hot crack formation. We find this very low gap and try to concentrate in it. So we also use a line beam shape because it's more common for aluminum. This is a video of our process. Okay, so it's also quite fast, something like 20 centimeters per 1 second to weld. And we also got quite nice thin. You can see almost no defects. And the UTS was also something 230 megapascal. That is much low, like for aluminum 7075, but it still was very nice because we not use welding wire. This is one more time results. We got 340 and 217 megapascal. This is our non-porosity results. Materials for bending, which also passed bending successfully. So generally, we can use this dynamic beam shape for welding of non-weldable types of aluminum and other reflective material. It is very common and very useful for this. Other type which I want to share with you, other case, is dissimilar aluminum copper welding. So connection and join from aluminum and copper is also not very easy thing because of this intermetallic composites. If we have mixing of aluminum and copper one inside of them, we have a lot of intermetallic composites which prone to cracking and just broke the welding seam. So for this welding, we use two types of welding in conduction mode and welding in keyhole mode. And I can say that it was also quite interesting. We don't success in keyhole mode. It is quite regular for laser, but we succeed with conduction regime. Why? Because there were no mixing because in this material. So how we use dynamic beam shape in this case? We divide our spot into two spots. This spot with more concentrate energy and other spot with less concentrate energy. So this spot with more energy we put into copper base and other spot with low energy we put in aluminum base. Why? Because of different temperature of melting of these materials. So we just melt them together and get very nice joint with intermetallic composites lengths of 130 microns. So it means in this length of intermetallic composites, our joint didn't broke. It didn't prone to cracks, and it's just not make some problems. So this is how we make the process. You can also see that the process is very, very, very fast. It's probably less than 1 second welding for all of the process. And we also checked our joints. It was stable on leak tests for 43 atmosphere and stable after 2,050,000 cycles after fatigue tests. Other type of dissimilar welding case was very similar to this. We tried it probably first inward. We tried it to weld titanium and inward. It was just some question from Israel industry, some military things. I have to don't say about it, but so we use the same technique, two different point, and here we can see titanium and inward. The same result. We have a very low intermetallic layer, less than 10 micrometers, and because of this, it's not prone to cracking in the seam. So we have now a lot of mixing, and this is our SEM phase analysis, which says that we have a raw titanium, raw invar, and no really mixing in these materials. Okay, 2 more minutes. So probably our last case for today is ultra high hardness welding. Some industry in Israel also asked us to check possibility to change MIG welding, traditional way of joining these materials, into the laser. Oh, sorry. In laser. And results were really impressed. Why? Because of heat affected zone was shorted in 5 times. So instead of 15 millimeters by MIG, we got 10 millimeters of heat affected zone. Tensile strength increased in 3 times. So instead of 500 in MIG, we use 1000. We got 1050 megapascal, and fatigue tests also was very successful. It passed all the types of tests. So one more time, it was 6 millimeters ultra high hardness steel. It's mean with carbon equivalent equal to 1. That is also called unweldable when I learn this thing and learn about carbon equivalent in the university. So we welded in one pass with wire feed. So here we can see a really weld, heat affected zone, and we also can see that any defects, any problems during this ultra high hardness steels. It is quite usually very challenging thing. Okay, I think that's all. 4.5. So I'm happy to hear your questions, guys.
Thank you very much, Dr. for extremely interesting presentation. Time to questions. Dear colleague, please ask your questions.
You didn't say about polarization of laser radiation in your experiments and influence of this parameter on the stability, quality, and so on and so on.
Unfortunately, I didn't hear you quite well. You ask about stabilization of weld pool, or can you just repeat? I didn't hear it well.
What kind of polarization of your laser radiation?
What's mean polarization? It's not TIC, it's a laser welding. We have 1000 nanometers wavelengths, continuous welding fiber laser machine.
Circular or linear?
Linear.
Did you use fiber laser?
Yes. It's fiber laser. So here in the picture, you can see a scarf, which laser born. And after this, you can see here a slight fiber, which is going on into laser cell. Here is the fiber, here is the scarf, fiber you can see, and the laser head, which we put in cell to produce these experiments.
Okay, thank you.
Thank you. So you can ask one more time, probably in Ukrainian or Russian in private or in message.
Okay, thank you. Some more questions, please. Okay, I have one question for you.
Sure.
Can you which limitation do you see for this method?
For beam shape, you mean?
Yeah.
So first of all, we have several limitations according to spot size, because beam shape can impact on the welding during for some probably 100 of microns. If our spot size is more than 0.5 millimeters, we can't really impact on the spot size because of just direct energy. Other type of limitation is power of laser. When we use less than 1 kilowatt, it's just direct energy and we can use it. So main limitation is a spot size and density of power, so our power.
Okay, thank you very much.
Thank you.
I have one more question.
Yeah, sure.
About shaping of beam. In Biological Laser Center, our colleagues make the similar investigation with welding of aluminum and another specific alloys with shaping of laser beam, but they use specific polarization model after output of laser beam, and using this multi-polarization model can change the shape of the beam, laser beam.
How do you think which way is better? Your ways when you change shape of the beam using different connection of fiber, or maybe another way of our colleagues from Germany? What do you think?
Okay, thank you for your questions. Really interesting question. So I don't think that there is some better way to make a beam shape, because they got one type of beam shape and we have different way to get it. But we can change it really during after welding. We can change during 1 second 10 different beam shapes. As I know, for other types, it's not possible. They need to change it a little bit before. So our method is just a little bit more simple, and it uses more software organization. So our way is more faster and simple to use. But because of this, we have a lot of problems, questions, and modeling system. So sometimes simple way is better. Sometimes complicated way is more good. Finally, we have to make some wobbling to avoid defects. And I am sure that both ways are working, but for every different case, we can find our champion here.
Okay, thank you. And one more question. What quality beam parameters you have in such combination? Maybe of BPP or M quadrat?
It's a M square way. It's like Gaussian beam, Gaussian single mode beam. So probably now it's the best way of beam quality. We avoid multimode beam and goes to Gaussian beam M square.
It's these parameters which you say about single fiber, or it's after a combination of each fiber. I think that these parameters could be changed.
Yes, as I said, we first have one beam. After this, we divide it into 32 different beams and one more times combine it. So these parameters is for final part, like for single part, what's going on from laser head, not from the welding scarf.
Okay, thank you. Thank you very much.
Thank you.
Thank you, Dr. Kowalewski. There is any questions? Thank you.
Thank you. And have a peaceful day.
Thank you very much. I suggest to invite our next speaker. This is Mikhail Babur. He represents our presentation on the semi-effect of heat treatment on the structure of the ferromangan aluminum frame silicium carbon alloy, additionally doped by nickel, chromium, and vanadium. Please.
Good day, everyone, dear colleagues. First of all, I want to thank you for such great opportunity for me to be here with you today. Everything is good, and I want to talk about new materials today. About new materials, we all need new materials. I like this version. Thank you. I like someone said that civilization development bases on the development of materials. Next, please. We always may have a lot of work because in any time we need materials that are should be more strength, less weight, and lower cost, technological materials which are uniform for different applications, which are good in economics, which are ecologically friendly and recyclable too. If we compare some characteristics we all know that maybe the main of them are strength and plasticity and specific strengths, and we compare these characteristics for most common used alloys. We should notice that the most strong materials are steels, titanium alloys, and something called advanced high-strength steels. There is some kind of material that's called lightweight high-strength steels, and it goes in this chart too, in this green one. What is interesting? Their plasticity level is the bigger, even it may be compared to low alloyed aluminum alloys, and their specific strength is comparable to magnesium-based alloys and even close to titanium alloys. So we may say that these are very interesting materials. And go next slide, please. You know what is this? Everyone knows. And I want to notice that these vehicles are using about from 10 to 50% of such lightweight steels in different parts of them. For example, even armor plates and frame parts of tanks, planes are made of this. This is my favorite picture. This crane liquor, it consists on about 80% of these lightweight steels. This part is fully made of them. Like also Starship, it contains about 20% of such material. Next, please. It's very economically attractive, I want to say. It's maybe even comparable to tissue welding equipment, because annual growth is about 7%, and we may see that only 15 companies all over the world are producing such materials. And they tell us that its market should be about $19 billion in 5 years, next 5 years. Consumers, the main consumers of these materials are United States and Europe. And Ukraine has many material base for producing this type of materials. Okay, about experiments. In wide understanding, these lightweight steels have such chemical composition from 2. If we make it more narrow, recent investigations are aimed basically on such compositions. So we decided to create our own composition, and to obtain such samples you may see in this chart. We used induction melting, sand casting, and this is the appearance of our samples. Next, please. What is interesting? We analyzed their microstructure, and it was almost obvious that it should be 2 phases. It should be 2 phases, austenite and ferrite. But we were wrong. We were wrong because there was no ferrite. But you may ask me, so what is this slight needle-like parts? I'll tell you later. We investigate them in S-cast state, after annealing, after quenching, and H-hardening. First of all, we may say that they may be very
hard and applicable. Some of these specimens even in S-cast state, what we may see from comparing our microhardness. The second important thing that thermal treatment destroys grain boundaries. It's somehow connected with temperature coefficient of thermal expansion, something like that. You understand what I'm talking about. Structure doesn't change in these two, almost in these two specimens after quenching. And we may notice that something precipitates after low temperature H hardening. For these steels, average temperature of H hardening is 550 degrees. And the average time of H hardening is about not less than 5 hours. We make these parameters lower and obtain such interesting structures. Non-doped basic alloy doesn't have this. And these two has. Go next, please. We try to investigate the position of chemical elements. So this basic alloy seems to be fully austenite. Even there are some silicon segregations, and we saw that it may prone ferrite formation. It didn't. So these are fully austenite. But after quenching, as soon as after H hardening, we may see that some carbides are formed. Somehow, we do not know why they, maybe they were not formed. They left from the S-cast or annealed state and didn't dissolute in matrix. We will solve this problem later. But what is interesting? In alloy, which has nickel and chromium, we saw some micro volumes which pointed to aluminum and nickel rich area. As you know, maybe in these steels, aluminum is the best friend of copper carbides, the most commonly important strengthening phases. Here it is. This is his structure, and he is precipitates. He precipitates there where aluminum rich volumes are formed. So somehow nickel, which is austenite stabilizer, didn't want to stabilize austenite, and he prones formation of areas reached with high concentration of aluminum. This is very interesting because we saw that chromium should make carbides with somebody, not nickel, because chromium is carbide precipitation forming element. He formed carbides later after H hardening and only at the correct grain boundaries where diffusion should be higher than in other volumes. So this is the first interesting part. Chromium sits in austenite matrix and doesn't form carbides unless something very something with very high defectness appears, and he goes there to form his carbides. Next, please. And vanadium micro addition gave us even more interesting picture. We thought that if we add a small concentration of vanadium, we should see complex carbides with vanadium and chromium, as it happens usually in other steels. But we didn't see it also. we didn't see it also, and vanadium carbides formed behind the grain boundaries and nickel aluminum rich volumes. Grain boundaries with vanadium carbides, it's good because these alloys have many problems with grain boundaries, and usually investigators try to precipitate something on these grain boundaries to make them stronger. They left after annealing, and chromium carbides also start forming on the most defective areas. But what is the last important point is that only with microdoping of vanadium, we may see formation of kappa carbides as they are, only after this. So we will continue our investigation later because we have a lot of questions, but I won't read this. I want to tell that I'm happy that we may cooperate now. I know that some of our chairmen also do some similar experiments, and I think that this thematic is very good, economically important, military. Military important and scientifically important too. And now, please, I need to say thank you. Next slide, please. This work was funded by National Research Foundation of Ukraine, and also my friends from Kyiv Polytechnical Institute helped with some investigation parts. So thank you, all of you also, and I would be glad to hear your questions.
Thank you very much for interesting presentation. We are ready for the course, ask your questions. Thank you.
Thank you very much for your nice talk. You showed a lot of microstructures and, as far as I understood, EDX mapping. But how did you follow the phase formation? What phases were formed after different types of treatment?
I didn't show this chemical composition tables because it would be very much time needed to explain this all. If you want, I may say that the difference between nickel concentration, for example, in those two areas was about 3 times, and after H hardening about 4 or 5 times. And the chemical composition of these carbide forming zones were related with composition of copper carbides if we change some iron concentration to nickel.
So your conclusions are based on the chemical composition?
Yes, also on them also. Yes.
Thank you.
Any more questions?
Thank you for your presentation. I have one question. How do you addition aluminum in your alloy?
Part by part. We melted some volume of iron scraps. Then we put manganese and ferromanganese, then put some part of aluminum, and repeat this 2, 3, 4 times, depending on the volume of liquid metal we want to obtain.
Okay, and how much aluminum in being alloy?
12% weight.
No, you have biggest aluminum in charge. You don't have 100% in aluminum in.
The aluminum losses were about 2%.
Okay, thank you.
Thank you too.
Maybe the questions. Thank you very much for interesting presentation. It's very interesting first step.
Thank you.
Let's move to other presentation. Next report, next presentation will be in online region. I invite Yuri Nikitenko with presentation evolution of liquid phase methods for growing molybdenum single crystals. Please. Here we are speaking. Wait.
Repeat. Dear colleagues, we present to your attention a report evolution of liquid phase process methods for growing molybdenum single crystals. In the 70s of the 20th century, unique properties of refractor metals single crystal were revealed. High plasticity, low absorption of gas, hydrogen, and its isotopes, resistance to recrystallization, creep, resistance to plasma and alkali metal melts, irradiation and thermocyclic effects, special mechanical properties, and other. Куда? Study were carried out with single crystal of different purity, including high purity and technical purity crystals. The applications of molybdenum and tungsten single crystal were predicted in the plowing industries. Builds for production of zone-clined refractory rolled products, foil sheets, wire bars, papers, X-ray technology, screens, anti-cathodes, electronics, targets for sputtering, crucible for growing single crystal of oxide and nitrates, electrical industry, contacts and wires, laser technology, mirrors for optical and X-ray lasers, nuclear and thermonuclear power engineering, thermal emission converters, elements of the active zone of the reactors, channeling particles, aerospace engineering nozzles. However, in the high melting point of these metals imposed strict limit on their processing conditions. Therefore, the main liquid fast methods for growing single crystals are not crucible methods. They are vertical zone melting and the Vernel method. Vertical zone melting, the characterization is characterized by slow movement of the molten zone with a controlled temperature gradient. As a result, a single crystal structure is formed and the bottom of the seed crystal. The Vernel method was originally developed to produce single crystal sapphires by melting powder in the hydrogen flame. However, its modification with alternative heating source made it possible to obtain metallic single crystals. For zone melting on electron beam was used of the heating source. The method is effectivity for growing single crystal of small diameter up to 20 millimeters. However, the attempts to significantly increase the diameter of single crystal were not successful. With increasing crystal diameter, it was necessary to increase the powder or electron beam melting. This led to an increase in the height of the molten zone and overheating of its surface layer. As is known, molybdenum is in the molten state is very fluid. Attempts have been made increase the diameter by modifying the electron beam zone melting method. First, electron beam melting method with zone clamping is not earlier. With increasing crystal diameter, more electron beam power must be invested to keep the bus in a liquid state. This leads to overheating of the liquid metal, lowering of the surface tension coefficient, and spilling of the metal bus. Second, peripheral cladding method. Several rods are attached to a cylindrical single crystal. The middle of the crystal always remained solid. As the diameter of the single crystal increased, stress increased in it, which led to its destruction. In practice, it was not possible to grow high-quality single crystal by this method with a diameter of more than 30 millimeters. The development of plasma arc heating source made it possible to create a new method of growing single crystal. This was close to the Vernel method. In this method, the plasma torch is installed vertically coaxial with the seed crystal. The plasma arc melts the end of the seed crystal and creates a bus into which drops of liquid metal fall if the consumable bar is remelted. As flows from the picture, the depth of the bus is equal to one side of the crystal diameter. The interface surface in shape is close to a paraboloid of rotation. When phantom crystals appear randomly on the side surface, they sprout into the middle of the ingot at an angle to the crystal axis. Analysis of this method shows that the use of a single head source does not allow flexible control of the thermal field of a single crystal. Large stresses arise in the crystal, which contributes to the increase in the number of dislocations, sometimes leading to the destruction of the crystal along the subboundaries. The first variant of the equipment showed its working capacity in principle. The installation had such characterization features: a single coil inductor and a set of consumable bars that are fed across the ingot. In the process of equipment operation, technological, electrical, and thermal problems of the developed equipment were revealed. It was possible to produce a notch large ingot, but of low quality. Next study of the process led to a complete modernization of the equipment. The main change was in the design of the thermal element. A cold wall was added and the inductor section were distributed over the interface of the ingot. The method has several in the principle different characteristics from the methods described above. First, the flexed control of the thermal state of the single crystal is provided by a high frequency heating source. As an aftermath, the stress level in the crystal is reduced, which excludes spontaneous crystal fracture, and the number of dislocation is reduced. The use of the high frequency heating source allowed not only to heat the crystal, but also to keep the bus from spilling due to levitation forces. And second, the crystal is formed by moving a local metal bus. The bus is formed under the influence of a plasma arc heating source. As the bus moves, the consumable polycrystalline bar is remelted under the influence of the plasma arc. In this way, layer by layer, the crystal is formed. As a result of scientific research, for the first time in the world at the Patton Welding Institute, the technology of growing super large ingots of single crystal of refractory metals, molybdenum, and tungsten was worked out. Production and perspective. Here is product made of molybdenum single crystal. It is an X-ray lamp anti-cathode. This is from our crystal. Molybdenum is also used to make mirrors for industrial KO2 lasers. It is assembled that mirrors made of single crystal ingot will have better refractory and can be used for more powerful lasers. Conclusions. Analyzing the development of single crystal grow methods for more than 70 years has shown that it is impossible to grow large single crystal using a single source of high temperature heating and large metal bus. The problem is solved by the use of less to heating source and the use of a local movable metal bus. a transformation of 3D additive technology, which made it possible to obtain ingots of 20 and 160 and 117 millimeter in size. Already today, due to the development and mastering of the plasma induction method of growing, a new opportunity to expand to the scale of production and application of molybdenum single crystal for laser technology has opened up. The work was supported by a project of the National Research Foundation of Ukraine and our international partners. Thank you very much for your attention.
I thank our speaker for interesting presentation. And dear colleague, do you have any questions to our speaker? Nothing done. Maybe in Kiev.
Yes, we have a question. Here.
Please.
In Ukrainian. А яким чином ви знизили вміст кисню? Молібдену.
Melting this inert atmosphere and
Летучий окислы. Летучий окислы молибден? Да, и вольфрама тоже.
maybe.
Thank you very much. Any other questions? Thank you for our speaker. And I propose comes next presentation. It will be in person regime. I invite Eugen Pechenko with presentation on electroslag remelting of variable cross-section electrodes using a two-circuit scheme. Please.
Good afternoon, colleagues. I would like to present my research on electroslag remelting of variable cross-section electrodes using a two-circuit scheme. Electroslag remelting process is widely used worldwide to recycle used rolls from cold rolling mills and continuous casting machines. However, a typical roll has a variable cross-section with a diameter that varies by almost half. Don't talk. Next slide, please. Thank you. If you use a roll like electrode, his neck have a smaller diameter, which means a lower melting rate. And if melting rate is increased, depth of liquid metal bus will increase too. This will result in different crystallization continuous and ingot along its head, and ingot will not be homogeneous in its properties. Therefore, using classic ESR scheme, it's necessary to form a consumable electrode of constant diameter from use roll to ensure a constant mold filling factor. To do this is necessary to cut neck and the roll of the roll and the way and welding his barrel together. Typically, is electrode consisting of 2-3 barrels welded together is required to make a new roll from an ESR ingot. Next slide, please. In a classic scheme, power supply is connected to the electrode and bottom plate. The oval circuit scheme is characterized by use of current supply mode, to which a second power supply connected. In this scheme, the current supply mode acts as non-consumable electrode. This makes it possible to break the rigid connection between temperature parameters and performance melting rate
of VSR process, and also significantly expands possibilities to control the thermal process occurring in the slag metal bus, which was difficult to achieve in the classical VSR. Current supplied mode makes it possible to heat the periphery of the ingot, change heat balance of the slag metal bus, and the higher power input to the current supplied mode, the lower depth of liquid metal bus. This increases the ability to control the volume and shape of the metal bus, and length of two-phase zone terribly affect metal quality. Please, one click. Thank you. This technology can be applied to remelting rolls using then unconsumable electrodes without prior preparation. Use of electroslag remelting current supply mold technology will significantly facilitate, reduce the cost, and speed up the process of remelting rolls. Please, next slide. Next slide, please. Thank you. To determine whether electroslag remelting process current supplied mold technology can be applied to remelting rolls, which are electrode with a variable cross-section. A remelting experiment was carried out on a model electrode. This electrode had the same cross-section change as the roll. The main objective of this experimental was to investigate effect of current supplied mode on the depth of the liquid metal bus. As filling factor decrease, power input to the current supplied mode be increased. Please, next. After each electrode section was melted, the shape of liquid metal bus was fixed using sulfurous iron. Templates were cut of the resulting ingot, and sulfur impressions were taken from the observe the shape of the liquid metal bus. The study of cross-section templates of the experimental ingot showed that the depth of the liquid metal bus decreased from 18 millimeters to 13 millimeters, with an increase in the power supplied to the current supplied mode. At the same time, melting rate decreased from 114 kilograms per hour to 110 kilograms per hour. Next slide, please. To analyze the experiment, and next, sorry. To analyze the experiment, data were transferred to a mathematical model of the current density in the slag pool. The difference in current density and therefore heating at the same voltage with a minimum filling factor and a maximum filling factor, shown this left in this area. It's electrode 18 millimeters diameter, it's low filling factor, and its maximum diameter electrodes 115 millimeters and maximum filling factor. Voltage in this modeling is constant. You will see that heating in the slag pool is a very big difference. Okay, to properly understand the impact of current supplied mode, let's consider the change of the current density in the slag bus with the change in the voltage supplied in the current supply section from 0 to 15 volts, please, one click, in 10-volt increments. As we can see, the current distribution changed significantly, especially in the ingot periphery. This is current supplied mode section, and you can see that heat transfer is in slag bus. Okay, The electrical parameters of the full-scale experiment were transferred to mathematical model. Please, next. Modeling result clearly shows that the current density in the ingot periphery differs by a factor of 2. Consequently, the amount of heat generated in the slag bus in this area will increase, which affect the profile of the molten metal bus. Taking into account the effect of current supply mode, it was determined that the melting process performance should be ensured by the power supply to the electrode. Since the influence of the current supply area on the melting rate is not significant, but it has a strong impact on the depth of the liquid metal bus. Please, next. In order to maintain a constant profile and depth of the liquid metal bus, it is necessary to create condition for uniform heating of the ingot periphery, which means maintain a constant current density at the periphery. At the same time, it is necessary to ensure the same process performance to supply power to the electrode. The result of the adjusted parameters of the mathematical modeling of the electroslag remelting of variable cross-section electrodes are shown on the slide. The melting parameters were adjusted so that the current density on the ingot periphery is the same during the entire remelting process, but constant. Next slide. Taking into account the first experiment and the mathematical modeling, the melting parameters were adjusted. With these parameters, the melting rate was stable at 120 kilometers per hour. And next slide. As a result, we have a constant process performance, and the depth of the liquid metal bus is 15, 48, 45 millimeters. The difference is about 10%. Thus, a constant melting rate and properly adjusted power on the current supply section ensures the same depth of the liquid metal bus. As a result of mathematical modeling and full-scale experiment, the goal was achieved, and ESR ingot with a constant high depth of the liquid metal bus was obtained after melting the variable cross-section electrode. And next, please. Okay, in conclusion, in this some little research. It's a potential of electroslag remelting as means of recycling spent rolls from cold rolling mills and continuous castings machines is investigated. The feasibility of remelting rolls without severing the neck and welding them into a single invisible consumable electrode using of electroslag remelting current supplied mold technology will be demonstrated. In this approach will facilitate and reduce the cost and speed up the process of spell rolls recycling. Thank you for your attention.
Thank you very much. It's time to questions. Please, if you have. Maybe in Kiev.
I have a question.
Please.
Thank you for your presentation.
Just a second.
Thank you for your presentation. My question is, if we need to remelt an electrode with a different cross section, for example, one part of the electrode made of smaller has a smaller diameter and other parts had a biggest diameter. So in this case, how you recommend us to remelt such an electrode? To start from the smaller diameter and finish with the bigger, or on the contrary, or it does not matter, and why?
Okay, thank you. If you please slide number 8, please. Okay, no, next. Next, please, slide. No, it's 8. Oh, thank you. Okay. If you see, if we start, it's number 3, where print factor less. I'm right your question, where electrode is small. In this case, need start with maximum power to the electrode and power to the current supplied mode makes be no more than half of powers in the electrode. Why? Because in start process we have a cooling with a bottom plate. In this height of ingot, be different crystallization than this ingot like at center or hyper. Okay, and answer your question. If we start with very small electrode, needs give electrodes maximum power, and power to the current supplied mode not be highest than half of power that you give on electrode. Okay.
Yeah. Okay. Thank you.
Thank you.
Maybe next question.
Thank you very much for a very interesting presentation. And as far as I understand, you investigated numerically only the current density field.
Yes.
So you solved the electrodynamic problem. And my question about your plans: do you plan to struggle with more complicated problem with, I mean, a heat and mass transfer in the tool and in
Yeah. Yes, it's for electroslag remelting process, modeling this process. It's have a big question. In the world is don't have model who content and electricity, magnetic and hydrodynamics. Thank you. With current supply mode is not no. It's because only who have current supplied mole, it's Photon Welding Institute. In short, it's
Thank you. As I understand, he used a very simplified model for resolve 1000. Thank you. Thank you. Thank you. Thank you very much.
Thank you.
Dear colleague, we have finished the first part of our program, these sections, and now we have short public break in 20 minutes. Тому ми знайшли такий варіант, навіть ми не використовували собі різні програми, а так само використовували статистику. В принципі, є потреба робити більш трошки фінансові. Це ж не це те, що кажуть, просто зараз зробити, що було, тому що дитина все, що немає програми, просто швидко, і це ж треба навчити. А він ще собі не виписати на себе. Тому ми були важні, і в принципі вирішили, що це не буде. А в принципі, для мене тут більше.
Електромагнітні сили рахувати, за допомогою цього модуля потім підставляти модуль гідродинамічний, ну, плюс там, що там, я не знаю, там, як це дивиться.
Так, там накладається гідродинаміка, циклі фізика, тому що, в принципі, з температури змінюються електричні і магнітні характеристики, такі там вивести. В принципі, я з моделі такі бачив, інформації, робили такі моделі, але не для такої кристалізації. І от якраз те, що ми кажемо, і магнітні полі, магнітне поле, електричне поле, і трохи таке картини. Але все одно там по припущенню, спрощенню, тому що все ж там я, а інакше не я. Бачите? Цікаво. Так, чого там? Так, треба тільки.
Ну да. Ну что? Недолго когда не третьего не поставили. Я говорю, там, наверное, мы себе смысл, что я делаю, потом говорится, нет,
Dear colleagues, we are going on our work. I'd like to invite our next speaker, Dmitro Gavrilov, with presentation, synergy, melt pool, geometry, metrics, and acoustic analysis for enhanced defect detection in GMAW and WAAM. The presentation will be in online format, so I invite speaker to start this presentation.
Hello.
Hello, I hear you, please.
Yeah. Good afternoon. Thank you for inviting me to participate in this conference. Let's start. Okay. All right. Can you guys see my screen?
Yeah. Okay, and hear you very nice. So let's go, please.
Well, great. So good afternoon again. My name is Dmitro Gavrilov. I'm the R&D scientist at Xeris Automation. Today, I would like to talk to you about the use of the melt pool geometry and the weld sound for defect detection. Weld discontinuities impair the mechanical properties of the joint. Often such discontinuities are defects and require rework. The weld must be ground off and rewelded. This process can be quite costly and time-consuming, potentially amounting to hundreds of thousands of dollars and many days of extra work. A potential solution could be a real-time defect detection system that warns the operator if discontinuity occurs. Immediate detection would help in identifying defects as they occur, reducing the need for extensive rework. It would prevent situations when the defects are only found after multiple weld passes, and the required grinding and rewelding is very significant. One way to create such a detection system is to use a neural network-based model that implements object detection or classification. Such a model would detect the presence of defects in weld camera stream on frame-by-frame basis, using each frame as an independent image. High accuracy of the modern deep neural network models and the ability of a single model to identify various defects are obvious benefits of such an approach. The major issue, however, is that to train a model to recognize defects, one needs to have a collection of images of those defects. The size of such a collection should be comparable to the size of good weld images. Furthermore, to achieve a model that can be applied to different setups and points of view, the training data set will have to have a decent variance of the defect images. In other words, it all comes down to having a large data set of weld defects from multiple sources, which is extremely hard to get. Another class of machine learning models is novelty or outlier detection. It is a group of unsupervised learning models that only require good data for training and then detect if the new data deflects from it. The data can be represented by any vector per unit time that carries some meaningful information about the weld. Since such models train on good samples only, they do not require a data set of defects. Typically, these models are much lighter compared to the neural networks models, so that the training process takes very little time. In some cases, it can be a fraction of a second. These benefits, of course, come with drawbacks. An outlier detector model cannot identify an event as a specific defect. It can only say that there is a variation from the trained data. In this work, we're going to discuss this second model type. The structure of the proposed model is shown here on the right-hand side. First, the good weld data is collected, and the feature characteristics are extracted from it. We're going to discuss these features in detail in the next slide. After the good weld data is collected, it is used to train the outlier detection model. The trained model then is run on live data, and the model measures how much the next portion of the data is different from the training data set. And if the difference is above a threshold, it raises an outlier warning. An outlier means that there is a variation of the data from what it is expected to be. The detected variation is that must then be expected, and as it may be caused by a weld defect. The weld data used in this work includes the melt-pool data and the weld audio. Experienced welders and welding operators, they closely watch the melt-pool, notice changes in its appearance, and focus on making sure the melt-pool looks exactly as expected. The operators and welders also listen to the weld. The weld sound is produced by the complex interaction between the waveform of the weld current, the arc length, the droplet detachment rate, and so on. Consequently, the weld sound is sensitive to variations in the weld parameters, detachment rate, gas flow, contamination, etc. The sensitivity of the melt-pool geometry and weld sound to variations, including those caused by weld defects, make them a natural choice for this model. Now let's have a closer look on the technical side. The melt-pool is monitored by a weld camera. Then the camera stream is parsed to the Zyris melt-pool AI semantic segmentation model that segments the melt-pool pixel by pixel, creating a detailed mask of the weld-pool geometry. This mask is then used to calculate multiple features, starting with simple things like width, height, area, and ending with sophisticated features related to the pool shape, like circularity, anisotropy, moments, etc. The weld audio, in its turn, is obtained with a microphone. In this work, we use the ruggedized weld mic. Analogously to the melt-pool width and height, there are audio features that characterize the sound. A change in the weld sound noticeable to an operator will be reflected in these audio features extracted from the raw audio signal. The features are then parsed to an algorithm called principal component analysis, or PCA. It reduces the noise in the data by reducing the number of dimensions in the input. And finally, the data gets to the outlier detection model. In our work, we used one-class support vector machine model. After training, the model analyzes the batches of new data as they come and raises an outlier warning if the new portion of data is different from what the good data, if it's different from the good data more than a specified threshold. Let's have a look at the examples. So the first case shown here is a video of a burn through. I'm going to show you this video that also has audio, so I hope you'll be able to hear the differences in the weld sound. The orange highlight on the top of the weld pool is the segmentation mask provided by the meld pool AI algorithm. I'm going to test the audio, and please tell me if you could hear the sound. Could you hear it? Was it too loud? Okay. All right, now after we've seen this example of a very bad weld, let's have a look at the results. This is the graph of the melt pool area in pixels measured using the segmented mask. The yellow colored area represents the training data. In this case, we use the first 11 seconds. The geometrical features are calculated on the fly, and after the train set is collected, the PCA and the outlier detector model are trained. Since they are so lightweight, the training takes a fraction of a second. On my laptop, only a few thousandths of a second, actually. So that the model is trained and run without any noticeable interruption of the video stream. The green areas are those that the model classified as inliers, or in other words, a good weld, and the red areas are those that differed from what the model was trained on. Now let's see what the melt pool looked like along this curve. In the beginning, the melt pool was a little large until it stabilized for a few seconds. But soon the first burn through occurred. The melt pool then tried to recover, but then the arc burned through the metal sheet again. After that, the melt pool could recover and stabilize again until the heat got accumulated in the workpiece and another series of burn throughs occurred. Here you can see how the first one looked, and the other four looked basically the same. Then the melt pool tried to recover again and could stabilize before the weld ended. Let's also have a look at the other melt pool features. So that the one we saw before was the area. Here we have the width, height, perimeter, second moments of the melt pool blow up, and other parameters that can be used to characterize the shape of the melt pool. As you can see, all of them were affected by the melt pool geometry changes caused by these burn throughs. This plot shows a combination of those features mapped by the PCA. This is how the outlier detection model sees this. Each of these dots represent a short interval. The X and Y axis are the first and the second principal components. As you can see, the green inlier points are closer to the yellow points from the train set with some margin, and the red outlier points are at a distance from the train data. Now let's have a look at the audio result. If you could hear the weld sound from the video, you probably notice very clear pauses in the weld sound when the burn-throughs happen. Those pauses are, of course, drastically different from the training weld sound, and they are clearly reflected by the audio features. For example, by the ones shown in this graph. As you can see, the burn-through moments were easily identified by the model based on the audio signal. The variations in the multiple shape produce smaller changes in the weld sound, and those differences were not detected by the model with the threshold used in this case. On the principal components map, the inlier points remained quite close to the audio train set, and the burn-through moments were at a decent distance from it. The second example I'd like to show you presents a weld contaminated with aluminum powder placed in two sections of the weld groove before the weld. The amount of aluminum powder was not enough to create a large distortion of the weld pool, but the weld sound in this case reflected the contamination clearly. Let's go look at the results again. In this case, the melt pool geometry was not significantly affected by the contamination. A certain change in the geometry, particularly in the second half of the weld, was present and was detected by the model. It is also reflected in the principal component graph. But on the other hand, the weld sound was directly affected by the presence of aluminum in the weld. The portions of the weld between 16 and 41 seconds and after 54 seconds on this graph here were correctly identified by the model as different from the trained data. Some traces of aluminum powder between these two sections had also some effect on the weld sound. The contamination led to formation of porosity in one of these weld segments. The graph of the principal components shows a group of points standing at a distance from the train set and the inlayers. This group of points represent the weld audio of the contaminated area. This brings me to the conclusion. We proposed a novel unsupervised machine learning model to search for novelty in the live weld data that may be caused by certain weld defects. The model uses the data extracted from the video stream by Zyris melt pool AI segmentation model for the weld pool geometry. Weld audio stream is processed and multiple features are extracted from it as well. And both those features are used to train, both those feature sets are used to train a novelty detection model that could successfully detect defects, such as burn through and weld contamination used as examples in this work. Thank you very much for your attention. Thank you to Dr. Schwab to inviting me to the conference, and also to Alexei Semenov, Oleg Maknenko, and other people I know. Thank you.
Thank you. I thank the speaker for interesting presentation. And propose ask your questions.
Thank you. Just questions about segmentation. Is it real-time segmentation? Do you use your own architecture of the model, or use UNet or YOLO?
Yes, this is a real-time segmentation. We used we do have some models which work with YOLO. This one is a different architecture. This one is called Light RASPP. It was lightweight enough to for us to be able to run it in real time, so it can be used on the actual real-time weld inspection.
And what is image resolution? So inside you have 2D image from camera and also 1D for sound. What are the dimensions of this?
That's another good question. Thank you. The resolution of the cameras can be different and depends on the well camera. In this case, it was the video from actually a thermal camera made by Zaris Automation. As being a thermal camera, has a bit lower resolution than our other well cameras. This was 512 times 640 pixels per resolution, and the model worked with the entire image, so it was 640 for the model.
And my last question, and for what welding processes your model can be applied? So you train only maybe arc welding. Can you apply this model for laser welding or other types?
So there in this presentation, yeah, maybe I wasn't that clear, but there were two machine learning models involved in this process. The one was that the one that made the semantic segmentation of the weld pool. This is the pre-trained model that, of course, will depend on the data that you need. So, and the other model is the more general model that can be used to defect detection without having seen those defects before. So that one is an unsupervised model that can be used on laser welding, arc, gas tungsten arc welding, gas metal arc welding, and other processes. We also tried it on audio signal only for submerged arc welding, because there, of course, like the camera is relatively useless. So the first portion for the multiple segmentation, yes, that has to be trained for the specific process. For now, we have versions for gas metal arc welding and for gas tungsten arc welding.
Please, the next question from the conference call.
Thank you for your report. Tell me, please, what kind of defects can you find beside burn through? And if possible, the minimum size of the defects?
So as I said, this model detects if there's a change in the data from what it was trained on. So it depends if there is a variation from the good well data. It cannot specify what kind of a defect it is. It can only tell you if there is some change that has to be inspected afterwards. So it can point you out some areas on the well that should be then inspected with the X-ray or some other non-destructive testing, something like that, for you to make sure that everything complies. But it will help you search for these areas and ignore those that are more likely to be good wells.
Okay, but if you use the control of the voltage or current during the welding, and then we can say it's okay or something wrong. If you compare your methodic with such usually used methodic, what is the better? What is your profit?
Current, yes, voltage and current are commonly used for this type of detection systems, and they do have their benefits, right? Like it is easier to collect the data from the welding machine directly. In this case, we use a different approach, as we believe that that the electric welding parameters are the cause, but not the only source of problems. So there you can have some contamination, you can have some variations in the gas flow, some other things that also may affect the appearance of the well pool and this welding sound, which are the result of this, and might not affect the weld parameters as significantly. So we believe that when if we try to enhance the and expand the current detection system rather than compete with them, we can bring some more benefit to it.
Thank you.
Thank you.
Maybe our colleagues in Kiev have something interesting. Okay. Okay. Oh, please.
Thank you for interesting presentation. And dear colleague, and my question about software you used. Please tell a little bit about software. Is it in-house software or national?
Yes, the software used here is the software made in-house by Xyrus Automation. It is commercially available at a separate license that comes with the purchase of the well cameras.
Okay. Thank you very much, Mr. Gavrilo. We will be glad to hear you. And now we come into next presentation.
Thank you.
Our next presentation will be in personal format. I invite to make his presentation Maxima Vdovina. This presentation on alumothermal recovery of vanadium containing waste in electroslag network. Please.
Good afternoon, dear colleagues. As a topic of my presentation, alumothermic reduction of vanadium content was under condition of electroslag smell. Next slide, please. Next. There are limited resources of natural rave materials containing vanadium in Ukraine. Therefore, man-made wastes are currently relevant source of vanadium. The process of producing vanadium from chemically enriched vanadium containing waste, where secondary aluminum is used as a reduction agent, final metal waste from various industrial as a filler in investigate. Next one. Vanadium from several oxygens, VO, V2O3, VO2, V2O5. The most interesting for recovery are V2O3 and V2O5. With increase in the degree of oxygen of vanadium, the acidic properties of oxygens and here chemical stability increase. The temperature dependence of the Gibbs energy of reaction of formation for VO and V2O5 oxygens is described by following equations. Next. silicon, hydrogen, carbon, and aluminum can be used to recover vanadium from oxides. Aluminum is a more interesting reduction. The reaction of vanadium oxides reduction with aluminum are exothermic. That signality reduces the cost of electrical energy and facilities and organization of the producing process. All other reduction options are endothermic process, and some of reducing agents are undesirable impurities. Next one, please. The charge of this process consists of vanadium pentoxide, aluminum powder, iron scrap, and calcium oxide as flux. The vanadium source, the technical vanadium pentoxide used in the charge has 86% V2O5. The reducing agent was aluminum waste with particle size for 0.3 to 1 millimeters. For alloy formation, iron powder with particle size fraction up to 1 millimeters. Lime and calcium fluid were used to form a slag pot. The amount of reduction agent is calculated according the stoichiometric coefficients. The reaction of vanadium reduction with aluminum is highly exothermic. The amount of other lime should be 48 to 53% of the amount of oxidized aluminum to obtain the lowest refractory effect. Next one, please. This slide show a follow chart of the ferrovanadium production process. Hooper mixing start of the process, charge melting, pure into mold, separation melt of products, storage containers. This slide present the schematic view of the melting in unit and demonstrate melting process extra view. The melting consists of three stages. First stage, solid start. Second stage, melting of the charge. Third stage, holding under current. The arc initiation thermite reaction and the new portion is added to the crucible as the charge melts. The reduced melts droplets settle to the bottom of the crucible under a protective layer of slag. Next. The electroslag melting process can be carried out with metal and slag discharge and on the block. You can see the view of the melting crucible with we use. Next one. The electroslag melting process can be carried out with metal and slag discharge and on the block. The series of experimental melts we carried you with different charge composition and power supply connection. During the exothermic experimental tests, the parameters of the technological process we adjusted in order to ensure the desired course of the process and to coating and alloy of the target composition. The composition of the charge of the experimental melting is given in the table. The chemical composition of the result metal of the series of metals in shown in the table. As can be at some test, the alloy has an increased carbon content because if this interacting with the bottom electrode material. Therefore, it was decided to resection the bottom electrode. The next mills we conducted and modernized sorry. Scrabble with refractory magnetic brick lines and steel bottom electrode. The polarity of power sloopy was also reversed. The chemical composition of the metal obtained during melting in the modernization Crosby is given in the table mills 5 to 12. Next. The results of the last three mills 10 to 12 have showed that the different parameters of the technology increase the stable production of an alloy with the target chemical composition. Each of the mills yielded an average of 7.50 kilograms of ferrovanadium, which is 50.35% of the total vanadium oxide on iron in the charge and 50.9 kilograms to slag. The extraction of vanadium into the metal was 85-90%. Based on the result of experiment melting, the electric mode on the other parameters of the technology were determined, which ensured the stability production of ferroalloy grades ferrovanadium 60. Examination of the slag under a scanning electronic microscope revealed the presence of metal droplets near the slag metal boundary with average size of 125 nanometers. Analysis of the slag in this zone showed that it mainly consists of calcium and aluminium oxygens with a small quality of vanadium oxygens. In the middle section, in the slag layer, tells its height. The quality and size of the inclusion discrete to 70 nanometers. The inclusion also contained a lowered amount for vanadium and higher amount for aluminium. Near the slag atmosphere boundary, the size of the metal inclusion fuse decrease to 10 nanometers. The studies have shown that the length of time a slag bot is held under current after completely melting of the charge affects the degree of reduction of vanadium pentoxide from the slag concentration, the degree of extraction of vanadium into the alloy with an exposure of 10 minutes. The final content of V2O5 in the slag 11.36% with an explores for explores for 15 and 20 minutes. It was 5.11% and 4.26. Нема. Next slide. Field scale study on the production of vanadium by the electroalumo process for chemically enriched vanadium contains waste using the electroslag process have shown that the reduction of vanadium oxygens in the slag layer with the possibility of supplying additional energy allows effective control of the reduction process intensity. Conclusion: the electroslag reduction process ensure high product quality and the possibility of waste-free production. The investment in equipment for this process is really low. Thank you for the attention.
I want to say thank you for our speaker and propose, because lack of time, I propose comes discussion of this report in personal conversation. Thank you very much. I will present you with participant certificate. Success. So thus we go into next. We come to next presentation, which will be in online regime. I invite Andrei Severin with presentation production of heat-resistant titanium-based alloys by electron beam melting in Ukraine. Please. You can start the presentation.
Народ освічений.
Good afternoon. My name is Andrei Severin, and today I would like to present you the report of production of heat-resistant titanium-based alloys by electron beam melting in Ukraine. The full-scale war increased the importance of providing the country with products of its own production, both military and civilian. One of the strategic direction of industrial recovery should be the development of titanium production industries based on it. Ukraine's reserves are estimated differently, but according to most estimates, they are the largest in Europe. According to the report of the US Geological Survey, in terms of titanium or reserves, Ukraine is in the top 10 of the world ranked, which 5.9 million tons of ilmenite reserves and 2.5 million tons of rutile reserves. These explored and developed reserves are enough to occupy a leading position in the world market of titanium products. The aerospace titanium market was estimated at $1 billion in 2022 and is expected to grow at a compound annual growth rate of more than 5% from 2023 to 2032. For example, Airbus aircraft production. In the A350 model, the mass fraction of titanium alloys is 13% of the weight of the airplane, while in the A320 model was only 3%. Next picture demonstrates how many titanium alloys are used in our domestic and family aircraft. Approximately 40% is used in aircraft engines. At present, heat-resistant industrial titanium alloys WT31, WT6, WT9, and WT20 are among the main materials used to low and high-pressure compressor of domestic engines, as well as in power engineering. These alloys were developed back in the 60s of the last century, but they are quite actively used. In high and low pressure turbines at temperatures up to 700 degrees, nickel alloys are mainly used. They can be successfully replaced by heat-resistant titanium alloys of the new generation. When ingots of titanium alloys are produced by vacuum arc melting, significant overheating of the melt occurs, a large metal boss is formed, and as a result, liquefaction and coarse grainy structure of the metal is obtained. In recent years, the technology of electron beam melting, ABM with intermediate power has significantly expanded the range of titanium-based alloys due to technology innovations and is currently almost as good as the production technology of vacuum arc melting. Thanks to the creation of shallow liquid bath, finer and more uniform structure is obtained. Electron beam melting allows to clean the metal from gaseous and non-metallic impurities. In order to study the quality of the metal and enhance the productivity of the process, the research was carried out on improving the ABM technology of heat-resistant titanium alloys in the Patton Electric Welding Institute. As a result, two mathematical modeling methods were used to calculate process parameter resulting in good quality ingots. Smelting of ingots was carried out in an industrial electron beam unit WR5810. This electron beam unit designed by Patton Electric Welding Institute allows to melt titanium ingots of various assortments weighing up to 20 tons. The following slides show only a small part of manufactured products. There are large ingots with a diameter of 840 millimeters of titanium alloy VT31 and their macro structure and chemical composition. Ingots with a diameter of 600 millimeters of alloy VT6 and 500 millimeters of alloy VT20. The macrostructure of all ingots and their chemical composition fully correspond to the standard. Next slide shows the deformed semi-finished products which were made from the obtained ingots at enterprises of Ukraine and used at enterprise of power engineering. A study of the mechanical properties and structure of the obtained forgings made from ABM ingots was conducted. The experiments show that electron beam melting is an effective method of obtaining high-quality ingots of industrial heat-resistant titanium alloys. ABM can completely replace the WRT process and the qualities and mechanical properties of deformed products made from them fully meet the requirements of the standards. One of the directions for improving the high temperature properties of titanium alloys is the creation of titanium composite based on the TL system with silicon content. Such composites have a multi-phase structure where the strengthening of the titanium matrix by the refractory compound T5C3 occurs during the crystallization process. Alloys of this system are developed by the Institute for Problem of Materials Science. These alloys are promising for creating a new class of materials with a high level of heat-resistant characteristics. Ingots of these alloys with a diameter of 110 millimeters were obtained at the electron beam furnace WRT-208. Chemical composition of this alloy is shown in the table. The metal structure of the ingots is equiaxial, dense, homogeneous, with no zones that are etched differently across the cross section of the ingots. There is no significant difference in the structure of the central zone of the casting and that of the peripheral zone. The macrostructure of the longitudinal template shows a small liquid bath during the entire melting process. Ultrasound testing did not detect any defects in the form of pores, shells, cracks, and non-metallic inclusions. In none of the obtained ingots, the segregation of alloying elements characteristic of warp ingots was detected. The study of the structure of alloys showed that they can be attributed to pseudo alpha alloys. They consist of packets of lamellae of alpha phase and a small amount of residual beta phase. Silicides are also present in the structure in the form of both whole layers and small secondary silicides along the boundaries of alpha plates. Work was carried out on the development of technology and deformation processing of ABN ingots of experimental alloy. Deformed semi-finished products with a diameter of 55 millimeters were manufactured. The optimal mode of deformation treatment of ABN ingots forms a mixed globular laminar structure where the alpha phase is present in both plate and globular form. The average grain size is 20-40 micrometers. A large number of silicides is observed in the structure, but they are quite dispersed and distributed between alpha plates and in the form of separate allocation along the boundaries and in the middle of alpha phase grains. A study of the mechanical properties of cast and deformed metal at room temperature and temperature of 600 degrees was carried out. Studies show that the plasticity of the material at room temperature compared to cast increases almost 25 times, and the high strength indicators both at room and working temperature of 600 degrees exceeds the level of the best world analogies. This indicates the potential possibility of using these alloys in aircraft engines of domestic production. And conclusions. The technology of electron beam melting with intermediate capacity provides guaranteed removal of titanium refractory inclusions of high and low density. Programmable power distribution of the electron beam on the surface of the melt allows affect the crystal structure of the ingot and allows to obtain ingots of various cross section. Technological processes of ABM developed in PVI makes it possible to obtain ingots of heat resistance titanium alloys that meet all the requirements for chemical composition and mechanical properties. Installed in State Enterprise Titan of Pattern Electric Welding Institute equipment allows to produce industrial batches of titanium ingots of various sizes to expand the score of application of titanium in various industries and to organize competitive production of ingots of heat-resistant titanium alloys in Ukraine. The production of semi-finished products from the titanium alloy ingots by electron beam melting is organized of the plants of Ukraine. Thank you for attention.
I sent the presentation, and we have short time for discussion. So,
I have a question.
yes, okay, please.
Please, thank you for your presentation. I have a general question about electron beam melting technology you used. My question is, what do you think the periodicity of this process, I mean that the liquid metal get into the mold periodically, not continuously, by a different portion. So such periodicity is an advantage or disadvantage of this technology. This is a positive or negative feature of melting technology.
We think it's positive because we have a small liquid bath.
Okay, so positive feature of this technology. Thank you.
Okay. Thank you. Next question, please. Okay. Thank you very much.
Thank you.
We come to next presentation. Our guest speaker.
Им надо было и нам писать. Это упущение.
Who can start your presentation?
Организатор.
Can you hear me? Давайте у нас выключение. У нас микрофон. Sorry. Dear colleagues, my name is Vladimir Barabash. I am a postgraduate student in Patton Electric Welding Institute, and title of my today's presentation is New Method for Improving Physical Homogeneity of Steel Ingots. Known that large steel ingots have a problem with axial porosity and cavities that form from, during metal solidification process. We consider as the main source of these defects its large two-phase zone, also known as Marsh zone. Produced defect you can see on the left picture. That picture of, if I recall correctly, 200-ton ingot. In order to solve this problem, we propose a new method for controlling the ingot solidification by applying combined external influence. Our method consists in a combination of external heating of the upper part of the ingot and periodical stirring of the liquid metal. First of all, we decide to make physical and numerical simulation. In the slide, you can see our equipment for physical simulation. These pictures was captured during simulation and show us three scenarios of simulation. On first, we can see ingot solidification without any external influence. On the second, solidification with heating of top part. And on the third, you can solidification and periodical stirring metal substance. As you see, there is a tendency more influence applied to the ingot during solidification, more better sterilization angle. After that, we conduct numerical simulation using COMSOL software. On the slide, you can see
solidus and liquidus lines before and after steering. There is a couples of pictures during no, for every steering phase. On the next slide, you can see charts showing us that using our method, we slightly increase total amount of time needed for solidification, but at the same time, conventional casting, comparatively to conventional casting, our size of our mash zone not more than 30%. Now you can see animation of this numerical simulation. This shows solidification and external influence. As you see, after each external influence, steering and heating, we decrease size or volume of two-phase zone. After physical and numerical simulation, using obtained experience, we conduct experiment with real steel using this scheme. Firstly, we remelt consumable electrode into a crucible, then pour it to sand mold, and on the third stage, that begin right after pouring, we start to heat and steer our solidification method. There is the general view of equipment used for experiment. And here is obtained ingots. First ingots shows conventional casting without any influence during solidification, and we can see gross defects on the top part of ingot. After second image show us experimental ingots with produced by same steel with heating and steering. As you see, we almost the ingot almost without defects. On this chart, you can see hardness for this ingots, and as you can notice that first ingots conventional don't have some points because it's was we cannot measure hardness in this zone. But on the second ingot, hardness decreasing is minimal. This on this chart, that's density measurements, and you can see this decrease, but it decrease only on 0.1 gram per cubic centimeter, which is total is 1.5% of all measurement. Based on this method, we also design equipment for our partners, and that equipment was installed in the metallurgical plant and working. Here you can see a video of its working and ready for sound. Ой. Okay. This video was prepared during heating phase, and to sum up, let me read conclusions. Proposed method of external heating and since effectively reduce axial porosity and cavities in large steel ingots. Both simulation confirm the ability of this method to improve ingot homogeneity by reducing the two-phase mass zone. Experimental results show that ingot produced using this method have higher metal density and improved hardness consistency throughout the ingot. This method presents a promising solution for industrial scale production of high quality steel ingots with enhanced physical properties. Thank you for your.
Thank you. Thank you for the presentation.
Yes. Thank you for your presentation. What gas did you use for steering?
Actually, what do you mean about gas?
How did you organize the steering?
Main point, first of all, thank you for your questions. And main point of this presentation, I can name a particular method that we used, but main point is this method proposed combination of two different techniques.
Method of steering
Did
you use?
I'm not sure about that. Я не знаю. Okay, in particular case, we use inert gas blowing, periodical blowing without removing heating electrode.
Можно перемешивать и ложкой.
But
Я спрашиваю, как вы перемешиваете.
Как угодно.
Не как угодно, я спрашиваю, как вы перемешиваете.
Inert gas argon, yes.
Okay, thank you.
Thank you.
Что вы делаете?
Questions in here?
Да можно. Я спрашиваю, как вы делаете.
Next question.
Yes, thank you for your presentation. I have one question. Your last slide show two electrodes. Yes, you use connection scheme of Bifilar.
In this particular device, yes, but we can say that for only for this large scale inputs.
Okay, and question about what is slack bus height? How much?
I cannot answer you at the moment.
Okay, and question about chemical composition, the slag that we use.
Chemical composition of slag. I also can answer you at the moment, but if you're interested, you can contact me. I believe you can find.
Okay, understand. Okay.
So next question.
Thank you for your presentation. My question is, what governing dimensional parameter did you use in physical simulation? It's very important to choose governing dimensional parameter. It should coincide with the appropriate values of real experiment. Correct me if I'm wrong. Thank you.
Are you asking about physical simulation? Yes.
Yes, I mean, maybe you used relay dimensional parameter or another.
I can say at the moment that our model of for physical simulation that scale it 1 to 10 ratio ingot maintain geometry similar to the ingot. If I recall correctly, it was 8-ton ingot geometry parameters. We just no, decrease size of it. All the sides, yes.
Chemical,
physical
parameters of material.
Sorry. We use sodium thiosulfate for this because it has similar mechanism of solidification like the metal, and it's greatly used in our other physical simulation and different sources, and researchers use it.
Thank you for answer.
Thank you. Any other questions? So we finished discussing the point, and comes the next. We have final. We have final presentation. I invite the next speaker, Sergei, to share this presentation, workplace of a cosmonaut welder for the former manual of electronic welding of objects in open space. So please, we wait for your presentation. You may start.
Good afternoon, dear participants. I want to tell you about some information about workplace of a cosmonaut welder for performing manual electron beam welding of object in open space. Space environment and lunar surface is a research field to derive new data on the fundamental characteristic of substances, as well as development of new industrial sectors and technologies. When measuring the near Earth space and moon surface, it will be necessary to perform mounting and, in a number of cases, repair restoration work. Here, welding is priority technological processes during fabrication of structures for space applications, which allows producing reliable joints of structural elements with guaranteed selling without lowering their strength and with preservation of their weight and size characteristic. The next slide. In this slide, you can see some short video about how formations zero gravity in the flight laboratory.
Yes.
The state of wetland sets lasts for 25 seconds. During this time, the welder in a spacesuit was to perform complex and coordinated work on welding. When working in a pressure chamber, i.e. in vacuum space, it becomes more difficult for a person wearing a spacecraft spacesuit to coordinate movements. The flow of information decreases, which in turn markedly affects the result of the work of the welding operator. In the next slide, you can see a short video from experiments on the fly laboratory. As you can see, the welding researcher loses the welding tool under microgravity. He cannot even stay fixedly in one place and make coordinated movements while holding the welding tool. It was quite obvious that the problem of stabilizing the body of cosmonaut welder, possibility of precise performance of quite complex movements by him, which ensure high quality welding in orbit, are some of the most complicated tasks in the overall complex for welding in space. During analysis of flight tests, the welding researchers, together with Boris Paton, came to the conclusion that it is necessary to develop a device which will allow rigidly fixing the body in one position and without moving, concentrate on performance of the technological processes. On this slide shows the first workplace of a cosmonaut welder was developed for performance of experiments in open space on board the Salyut 7 station. It was made according to all safety and ergonomic requirements. Also in this slide shows how the cosmonaut performs coating deposition in open space outside the Salyut 7 orbital station. You can also see samples of welded joints made as a result of conducting this experiment in open space. The cosmonaut welder workplace allowed performing the technological operations of welding, brazing, cutting, and coating deposition for 3 hours and 35 minutes in open space. Workplace was oriented in such a way relative to the site of Salyut 7 station that when the electron beam unauthorizedly cuts a hole in the sample, or it will pass by the board with the samples. The beam should automatically switch off so not to burn through the space station hull. The experiment shows, first, the possibility of performance of the operations of welding and related technologies processes with the electron beam tool in open space. Secondly, that the operator wearing a spacesuit can safely perform complicated manual technological operations when using the workplace and obtain sound results. In the next slide, some information about in 1991-1992, universal hardware was used to perform a series of technology trains on welding samples from aluminum and titanium alloys, as well as stainless steel on the ground, as well as under microgravity conditions in KS-135 flying laboratory, Johnson Center, NASA, Houston, as well as 6 immersion in a water immersion facility at the Marshall Center, NASA, Huntsville, and 5 ascents to 6 kilometers in a pressure chamber. Generalization of the accumulated experience allowed development of an all-purpose complex of electron beam tool universal decision for operation as part of future large-size long-term orbital space stations. The decisions for taken together with NASA to conduct the International Space Welding Experiment on US Columbia spacecrafts. During preparation of the international welding experiments, the Patton Welding Institute decisioned and manufactured the hardware with a special platform. Attached to the platform was the hardware required for experiment performance, drum carrying the samples and container for replaceable samples, and the adjusted operator workplace. All that the cosmonaut welder workplace was developed to accommodate the US space suit. Appropriate changes were made in the decision of this auxiliary equipment to enhance the reliability during experiment performance and to strictly observe the safety regulations. In 1998, it was planned to conduct on board the Mir station the welding experiment, which was not performed on Columbia spacecraft. A new workplace was decided and manufactured for this experiment named Flagman. In view of the limited work space at Mir station, the workplace was very compact, but fitted with all the necessary elements for experiment performance, and it was called the workstation. The next slide shows numerous hardware tests in the flying laboratory and the pressure chamber. This is also unique footage taken during testing. Unfortunately, this international experiment was not conducted. In this slide shows two models of the workstations. First one later on improved, which was shipped to Mir station. After this works, we had two patents were granted for the welding operators workplace in the USA and Ukraine. The availability of patents once more confirms the importance of development and application of this equipment. When exploring the moon, much attention is paid to the creation of long-term lunar bases and infrastructure for these structures. Therefore, during human exploration of the moon, development of specialized electron beam welding hardware and auxiliary equipment, which is the cosmonaut welder workplace, is highly relevant. The decision team of Space Technologies Department used the modern component base and new materials for development of the cosmonaut welders workplace, meeting the requirements to space hardware. And conclusions during performance of operations in open space and on the moon surface. In order to conduct the process of electron beam welding, the specialized workplace of cosmonaut welder must be part of the overall hardware complex for working in space. Solving this problem, always fixing the body of cosmonaut welder, that it requires to precise coordination of complex movements, ensuring sound and stable manual electron beam welding in orbit or on the moon surface. Thank you for your attention.
Thank you for your presentation. Yes, now we can discuss the information, please.
Thank you for interesting presentation. What do you think? Is it possible to use such workplace for robotic welding in open space?
Thank you for your question. I think that workplace can be used with robotic method, electron beam welding, because workplace must be in the surface of spacecraft for the для встановлення. To mount, yes, sorry. For the mount, the automatically robotic electron beam equipment on the surface of spacecraft.
Thank you.
Thank you. Next question, please. Okay, we have question in conference call.
Thank you for your talk. I have a question. What is the maximum thickness of the material, aluminum alloy, you can weld using your equipment?
Thank you for your question. If we say about the electron beam equipment or workplace, or about workplace. If about workplace, electron beam welding was with workplace for cosmonaut welder. In these experiments was welded materials titanium, aluminum alloys, thickness 1.5 millimeters. If about the electron beam equipment we have a decision and produced, our equipment can be weld the aluminum alloys of thickness 8 millimeters and titanium alloys 4 millimeters.
With accelerated voltage 10 kilovolts.
Yes, 10 kilovolts. Yes.
Okay.
I'm sorry. Thank you.
Any questions?
No questions.
Thank you. Thus, we have finished our program for today. So, yes, of course. I have special information for participants.